Assalamualaikum warahmatullah. We are in the second part of chapter 1, consumer theory. We have done the first part, that is the introduction to utility function. And the utility function that you saw previously is basically a normal utility function. When I say a normal utility function, it is a function of consumptions of goods or commodities. Or in other words, it's just a real value representation of people's preferences and preference rankings. So just imagine if you have preferences over certain number of commodities and then outcomes, and a utility function here tries to represent that as a function, okay, mathematically speaking, so that we can use useful properties of the real numbers to model choices and tackle problems. So this is what I said to you just now. So when we talk about ordinary utility function, the ordinary utility function is denoted as u as a function of x. Remember, if you see x here, it refers to many bundles of goods and services that yield the same level of utility. Okay, so x, x1, x2, until the last one, xn. Okay, so the ordinary utility function ux represents the consumer's preferences directly. Why? Because it is a function of the good that we consume. So if you consume any bundle of goods, okay, let's say bundle x1, bundle x2 or whatnot, then it gives you a certain level of satisfaction or utility. So your utility, the level of satisfaction, is directly being affected by the amount of goods or commodities that you consume in each bundle, and it yields the same level of utility or preferences. So this is what we call as direct utility function. But then we have another types of utility. We call it the indirect utility function. So what does it mean by indirect utility function? It is basically a kind of utility function. Okay, it is a utility function at which we have the maximized value of utility given prices and also income. So in this case, prices and income are the exogenous parameters that affect the indirect utility function. So why do we call this as the indirect utility function? Because I'll show you in a bit later. So let's say we call indirect utility function as V. Okay, I told you just now that indirect utility function is basically as a function of two types of parameters, prices and also income. If you look at P here is a vector because we have different types of prices depending on different types of goods. So P1, P2 until Pn. Okay. So here, this is an indirect utility function. How do we get an indirect utility function? The indirect utility function, the first thing that you did previously was solving the utility maximizing problem. Remember, we have the optimization problem. And then after that, you will find the individual demands for goods given the prices he faces and also his income. And then after that, in order from here, then you have what we call Marshallian demands, isn't it? So you have seen the meaning of Marshallian demand in the previous video, but once you have these results of Marshallian demand, after solving the utility maximizing problem, you use these Marshallian demands of, let's say you have two goods, you found the equilibrium for good one and also good two. Yeah, this X is not referring to bundle, this X refers to good. Here refers to bundle, or instead of this, in order not to make you confused, let's say we have good let's say Y and Q, for instance. So you have good Y, you have good Q, and these two combinations of goods, this bundle give you the maximum utility. Okay, and then you put this back into the utility function here. The original utility function. So you have U star as a function of Y star, Q star, not this, yeah? And this one, you know that U star is actually a function of good Y. Good Y is a function of price and also income, isn't it? And also the second one, good Q, as a function of price and income. Okay? So now, once you plug in the optimal level, then it becomes indirect utility function. So here, look at the definition. Definition 10. The function obtained by substituting the Marshallian demands in the consumer's utility function is what we call the indirect utility function. So this is the formal definition of indirect utility function. So indirect utility function here is called V as a function of price and also M. Okay, it's not directly as a function of bundle of goods that we consume. But then this indirect utility function can be rewritten as using the direct utility function. The direct utility function is a function of goods in which these goods are in bundle X, and bundle X here depends on a vector set of price and also income. So alternatively, we can have indirect utility function written as this, equivalent to utility level that is maximized subject to budget constraint. So in summary, it is actually the maximized value of utility given prices and income. All right, now let's move to the next theorem, which is theorem number 4. And this theorem shows you some characteristics of indirect utility function which are very pertinent. It says if the direct utility function, which is u as a function of x here, is continuous and also strictly increasing on the set of a real number, non-negative real number with the n number of commodities, okay, then the indirect utility function as a function of price and also income is actually, number one, continuous on this plane, okay, on this dimension. All right, now this dimension is actually, you see the first one and the second one here. The second one here I don't have to explain to you, yeah, and the first one here is actually the set, and this set here is basically in which if we have a direct utility function which is continuous, then that means the indirect utility function, which is a function of price and also income, must have the value of price which is much greater than 0, and also the value of income which is much greater than 0 as well. Okay, that means it is purely not only non-negative, no 0 at all, in within the set of n commodities here. Okay, so number 2, the indirect utility function must be homogeneous of degree of 0 in price and also income. Number 3, strictly increasing in income. Number 4, non-increasing in price. Number 5, quasi-convex in price and also income. And lastly here, it must satisfy Roy's identity. That is, if indirect utility function is differentiable at this particular price and also income, and then when we take the first derivative of indirect utility function with respect to income is not 0 value, then we can have this expression. I'll explain to you one by one every single character here that is outlined in theorem 4. All right, now before I proceed, if you look at 3 and 4 here, this basically relates to what we call monotonicity of indirect utility function itself. Okay, now so let's look at the second one here, because when it says continuous, it means it is differentiable, yeah, so I don't have to show you how to get this. But let's look at number 2 here, homogeneous of degree 0 in prices and also income. What does it mean when we say that indirect utility function is homogeneous of degree 0 in price and also income. It means when we double our income and also prices, doubling income and prices does not change the utility. So how do we prove it? Basically, if we take any constant or a scalar, call it t, and t has to be non-negative, then if we multiply the price and also the income by t amount in the indirect utility function, it will always give us the same indirect utility function like this. Okay, formally or theoretically speaking, so you can see here in this indirect utility function, we multiply price by the amount of t, we do the same on income m, and then this is what happens because indirect utility function is actually, the maximum direct utility function subject to expenditure equals to income, isn't it? So when we do this, it has to give us the same results of indirect utility function. It doesn't change. Let's use the Cobb-Douglas function that you have seen as an example in the first video. And if I were to rewrite it again here, the previous Cobb-Douglas function looks like this. So the direct utility function is actually x to the power of alpha times y to the power of beta, such that alpha and beta are between 0 and 1 inclusively, and alpha plus beta must be equal to 1. And then when we did optimization for this consumer behavior, we found the optimal level of x, call it x star, alpha m over px. We also found this optimal level of y star, which is beta m over py. Okay, so these two are what we call Marshallian demands that is derived from the optimization of direct utility function. So from here we can get indirect utility function. Now indirect utility function is a function of a vector of prices and also income, isn't it? So in this case specifically, it has to be the x value at the optimal level that we found using the direct utility function here, multiplied by the optimal level of y. So specifically, we can write it this way. So alpha m over px to the power of alpha multiplied by beta m over py to the power of beta, isn't it? So this is the indirect utility function. It is, a function of Marshallian demands for x and y. If we simplify it further, then we can have this: m to the power of alpha plus beta over px alpha times py beta, and then we have what? We have alpha to the power of alpha multiplied by beta to the power of beta. So this is our indirect utility function. Now, because we want to show that this indirect utility function is homogeneous degree of 0, then what should we do? Like I said earlier, if we go back to the previous slide, we must multiply prices vector and also income here by the amount of a constant or a scalar, call it t. Right, so how do we do it here? So by multiplying this indirect utility function by the amount of a constant, okay, then let's call this new indirect utility function as v new. So how do we do it? Let me use different color, that is blue. If you see here, the indirect utility function consists of this and also this. So the first one and the second one. The first one consists of M, income, and also price of two goods, X and Y. But the second one here consists of constants. So what we do is that for the utility function, we need to multiply by the amount of constant, call it lambda, instead of t I use lambda. And then constant here, the second segment here, still the same, that is constant, alpha to the power of alpha, beta to the power of beta. And then what we need to do is that multiply m by lambda, then the whole thing here to the power of alpha plus beta, and then divided by multiply price of x by lambda, then the whole thing here to the power of alpha. Do the same thing on the price of y, then to the power of beta. Now, what we can do here is that we write again the constant, take out lambda, lambda becomes lambda to the power of alpha plus beta times m to the power of alpha plus beta over, take out lambda, lambda to the power of alpha times px to the power of alpha, and then take out lambda here from py here, take out, and that becomes lambda to the power of beta, and then py to the power of beta. Now, these two basically can be rewritten as this, alpha, beta to the power of beta, lambda to the power of alpha plus beta, m alpha plus beta, and then alpha, because alpha lambda multiplied by lambda alpha to the power of alpha multiplied by lambda to the power of beta can be rewritten as this, lambda to the power of alpha plus beta. Then we have p x to the power of alpha times py to the power of beta. Let me use red pen. If you see this, they are the same, isn't it? So if you cancel them, it becomes 1. So basically, if I rewrite it again here, okay, because I don't have enough space, then we can have alpha to the power of alpha beta to the power of beta times m to the power of alpha plus beta over px to the power of alpha, py to the power of beta. What happens to lambda here? When it becomes 1, because we cancel it, 1, that means lambda here is to the power of 0, isn't it? So when we say that lambda is to the power of 0, you look at the power here, this power is 0, shows us that the indirect utility function is homogeneous degree of 0. And furthermore, when it is homogeneous degree of 0, when you multiply any, indirect utility function by a constant, it will give it the same results as the indirect utility function itself. So here you can see clearly this one is the same as this one, isn't it? Because this one is actually the same as this. So that's what it means by this characteristic, when the utility function is homogeneous of degree 0 in prices and also income. So we have doubling income and prices. It's not changed the utility at all. All right. Now, let us move to the second part of the theorem. We need to prove number 3 here. What is number 3? Number 3 says the indirect utility function has to be strictly increasing in M. And this is a part of monotonicity characteristic of the indirect utility function. So how to prove it? Now, when we say that the indirect utility function must be increasing with the level of M or income, that means if income increases, the indirect utility function must increase, isn't it? So that means the marginal utility will increase, okay, due to the change in income. So it's not the indirect, it's the marginal utility. Let me fix it here. So when income increases, then the marginality must increase, because when we say this is the mathematical terms, strictly increasing in M. Strictly increasing in M, mathematically speaking, it is like, upsloping, something like that, isn't it? With respect to M. Then that means when we differentiate the indirect utility function with respect to income, it has to be positive. Okay, so we must prove that. That means if we differentiate the indirect utility function with respect to M, it must be positive. This is the thing that we must see. Okay, so how do we do it? How to prove that it is positive? All right, now what we need to do, like I said to you just now, is that we need to differentiate the indirect utility function with respect to income, or M. Now look here. So we have the indirect utility function. The indirect utility function here is no longer as a function of, a vector of commodities, but it is a function of price and also income, isn't it? That's why it is called indirect utility function, because it's not directly, being affected by the commodities. But if we have direct utility function, we know that it is a function of income. It is a function of the goods in the bundle itself, isn't it? Many bundles. All right. So we call it UX, for instance, where X here is the vector that contains, a number of good 1, number of good 2, number of good 3. So X here, we call back from the last videos, vector contains x1, x2, until xn. Okay, bundle here. So we know that when this utility is at the optimum level, then, the direct utility function is at the optimum level, that we can have U as a function of X. And then we get the Marshallian demands, isn't it? And then Marshallian demand, let's say this bundle here, this is a bundle, and this is not good. So the bundle here will be as a function of price and also income, isn't it? You have seen it earlier in the Cobb-Douglas function. Let me recall back. When you found X star and also Y star, it is a function of M and P. So what you did just now is that put it back into the direct utility function like this. Then you get indirect. So here, X here is a function of price and income. Y here is a function of price and income. These two contributes bundle. Okay. So here, what we can say here is that at D equilibrium, U is a function of X star, and X star itself is a function of this. And when we write it this way, this one is what we call the indirect utility function, isn't it? So this one is actually the same as U as a function of, optimal level of bundles, in which optimal level of bundle is a function of price and also income, a vector of price. So because a vector of price here means consists of P1, P2 until Pn price, depending on how many commodities, how many N. Okay, so what should we do here? Like I said to you just now, we need to prove that if there is a change in income, okay, there is one unit change in income, then we can show that the marginal utility is positive. Okay, so here we need to differentiate the indirect utility function with respect to income, and we need to find the answer is positive. So how do we do it? Now here, the indirect utility function, we know that it's also can be rewritten as this. So now, when we differentiate the indirect utility function with respect to income, that means we also differentiating this with respect to income, isn't it? So delta U x star PM over delta M, isn't it? Okay. Now, next, because the indirect utility function is a function of direct utility, okay, of a commodity, of a vector of commodities, and the vectors of commodities here, the optimal level, depends on price and income. Okay, you can see that income is here, not straightforward here. So what do? And we know that x here is a vector containing of x1, x2, x3 until xn bundles. It's not just one bundle. All right. So when we differentiate, we don't just differentiate vector, because let's say you have x1 PM, isn't it? x2 PM. So you have many, bundles that also depends on price and income. So how do we do it then? It's not very straightforward. So here, when you differentiate it, you are basically differentiating a sum of bundles with respect to income. So this is how you do it. So when you differentiate it, you have to differentiate each and every one of these rather than one vector as one. So the sum of differentiate u with respect to x, because you cannot differentiate u with respect to m directly, because here you can see the direct utility function is a function of x star, but x star is the function of m. So u here is indirectly a function of m. Then in order to differentiate, we need to use what we call chain rule. So delta u over delta, not delta x, but delta xi. Okay, because I here refers to 1, 2, 3, 4 until 5 until n, times delta xi over delta m. Okay, that's how we do it. So that means this one is actually, if I try to, segregate it, then it becomes du over dx1 times dx1, delta x1 over delta m, plus delta u over delta x2 times delta x2 over delta m, plus until delta u over delta xn times delta xn over delta m. Then, because all of these are summation of repetitive thing, but for different bundle of goods, for different goods here, then we write summation like this, delta u over delta xi. Okay, good 1, good 2, good 3 until good n. All right. So we have the summation of the change in utility due to the change in income indirectly, okay, for each and every commodity in the bundle at the equilibrium position. That's what it means. All right. Now, after that, we haven't proven that this derivation of differentiation is positive. So what should we do now? If you can recall back the direct utility function when you did FOC, remember? So the direct utility function, when you did FOC, you have u as a function of x, isn't it? And then x consists of x1, x2, x3 until whatnot. Then when you did the FOC, subject to, income and also total expenditure. So we have FOC something like this. You look at video 1 here, delta u over delta xi minus lambda over pi equal to 0, isn't it? So if you have 1 delta u over delta x1 minus lambda p1 equals to 0 until you have a lot here, delta u over delta xn minus lambda times pn equal to 0. Remember that? Okay. So we use generic form rather than writing x1, x2, x3. So we use this generic form. Then this one can be written as delta u over delta xi equals to lambda pi. Now, if you can see this clearly, this one is actually this, isn't it? So what can we do? Let's call this one equation 1, call this one equation 2, call this one equation 3, and then call this one 4. What you can do is that substitute 4 back into 3. Okay. Substitute 4 into 3 yields what? When you substitute 4 into 3, it yields something like this. So we have this, yeah? Delta V py over delta m equals to what? Equals to the sum, okay, of I from 1 up to n, yeah, because we have n commodities. Substitute it, then we have lambda pi, okay, and then multiply by delta x over delta m. So delta x over delta m. Okay. And another thing that we need to realize is that recall back budget constraint is something like this, isn't it? Because we have good x1, x2, x3 until xn. So we have p1, x1 plus p2, x2 plus until pn, xn equals to m, isn't it? Now, remember, because we want to look what happens to our x1, x2, x3 if m changes, yeah, or income changes, and then after that, what happens to the utility, indirect utility, then what can we do on this budget constraint? Let's call this budget constraint equation 4. Is it equation 4? Let me check the number. Equation 5. So I did this, I call it equation 5. Why do we need to look at the change in good x1, x2, x3 until xn when there's a change in income? Because it has something to do with this. Okay? So how do we do it? What should we do with 5? So 5 here, what we need to do is that we need to differentiate 5 with respect to m. So differentiate 5 with respect to m, we get something like this. I don't write whatever in the middle here, but you have to write it, yeah? Because I say it out loud when I teach you, but you have to write whatever I say here. I'm trying to differentiate budget constraint here with respect to income. Okay, so how do I differentiate it? P1, P2, P3 until Pn are constant because prices are given in the market. So what we do here, P1, okay, delta x1 over delta m plus P2 delta x2 over delta m plus until the last one, Pn delta xn over delta m equals to what? When we differentiate, this function with respect to m, 1, isn't it? Basic, yeah? So here, that means because all of these are x1 until xn, then we can simplify it as this way. The summation of 1 until n equals to pi delta xi over delta m equals to 1, isn't it? Alright. Now, we can actually use the last expression here, put it back into this. Okay, so this one, let's call this one for A. So what we need to do here is that, let's call this one 6, substitute 6 into 4A, so we can get something like this. So we have delta V over delta M equals to, if you see this lambda, we take it out here because it's a constant, so summation of lambda is always lambda, any number of constant number, and then the rest is the summation line, summation symbol, and then pi multiplied by dx over dm, which is equation or expression 6, isn't it? So here, when we substitute 6 back into 4, then we can have something like this. Lambda, the summation, I equals to 1 up to n. Okay, I rewrite it again here. Pi dxi delta xi delta m, okay, equals to lambda times 1. Why? Because expression 6 here says the whole thing here is actually equivalent to 1. So this one is actually equivalent to 1. Then we get this. So finally, this implies delta V over delta M is actually lambda. And lambda itself, if you can recall back in the first video, it has to be positive, isn't it? Okay, by condition, remember? So what does it mean by this lambda? You see here, if there is a change in income, how much is the change in the indirect utility here? The change is by the amount of lambda, and the change is positive. That means if there is an increase in income, our utility will increase positively, and it's logic making sense, isn't it? How do we call this in economic? This is actually marginal utility of income. Okay, so that means the indirect utility function is strictly increasing in M, means marginal utility of income must be positive, and it does make sense. And at the same time here, I would like to emphasize, because we're dealing with the optimal level of utility, therefore lambda here we can put optimal level of lambda. I put star here to show that it is at the optimal level. So we can see clearly the indirect utility function has to be positively related with the level of income. Now I want to show you the proof for number 4. I did mention that the indirect utility function is non-increasing in P or price. Yeah. So this is another monotonicity character of indirect utility function. So let's say we have two different prices. The first one is P prime, the second one is P. Okay, the vector of prices. And let's say vector of prices P prime is more expensive or equal to the current prices. Then, logically speaking, the indirect utility function with the P prime vector is less or equal to the indirect utility function with P vector. Logically speaking is, no one is happy to consume any kind of goods with, which is relatively more expensive, isn't it? So how to prove it? So we need to have two sets of bundles or vector here. The first one is B, the second one is B prime. So let's say B here, a set of vectors of goods or commodities evaluated at the expenditure, the total expenditure equals or less than M or income. And we have another set here, B prime, which is X also, but evaluated at different total expenditure because of different price, which is P prime, but still less or equal to income. And because P prime is more or equal to P, then this second set here is in the first set, isn't it? Logically speaking, the second set is in the first set, so the first set is B. The second set here, perhaps here, B prime. Why? Because now it's relatively more expensive. With the same amount of income, the set here of bundles that you can have is less than B. That's what it means. And this implies if you have, optimal level of utility or indirect utility function, this is V, with price of P, okay, in the set of B here. So this utility must be higher than the indirect utility function in the set of B prime, isn't it? Why do I call this one indirect? Because we have the word maximum here. So maximize direct utility means we want to achieve indirect utility function. So logically speaking, the indirect utility function with lower price, which is P, gives you more utility or at least equal to the indirect utility function, which is V prime, with higher price. So I should put P prime here. So that it looks sensible. Okay, so that's proof. That's the proof for number 4. And the next one is we need to show that this indirect utility function can satisfy Roy's identity. So it says that if indirect utility function is differentiable at certain price, call it P0, and also certain income, call it M0, and at the same time, when we take the partial derivative of indirect utility function with respect to income is not equal to 0, then we can have this Roy's identity. Now, if you look at the Roy's identity here, you look at this requirement, why it can't be equals to 0? You imagine if this one equals to 0, mathematically speaking, what happens to this answer? It will always give you minus infinity, isn't it? And this one is X, I, okay? The amount of good at I consumed at the optimal level. So it's not infinity, it can't be infinity. So that's why the first derivative of indirect utility function with respect to income cannot be 0. Now, let me show you the Roy's identity here. What does it mean? Now, Roy's identity says that the consumer's Marshallian demand for good I is actually the ratio of the partial derivative of indirect utility function with respect to P and M after a sign change. Okay, after a sign change. So if you look here, it is a ratio of partial derivative of indirect utility. The indirect utility is written as this, isn't it? Okay, let's say at price P naught and M naught. Yeah. And if we take the partial derivative of indirect utility function with respect to price of I, then this is how we write it. Okay, this one I'll explain to you in a bit. Okay, now I want to focus on the left hand side here. Now, if we take the partial derivative of indirect utility function with respect to income, then this is the way we write it. And then we take the ratio between these two, then this is the way we write it. Okay, and then we have minus sign here, don't forget. What it implies is that when you take the ratio of these two different types of derivatives, then you can get the Marshallian demand for good I. In order to do this, we need to use what we call envelope theorem and Lagrangian method. So what does envelope theorem say, and why it is important to show to be used to show Roy's identity? So when we talk about envelope theorem here, I want to put it in a simpler form because I'm not teaching mathematics here, yeah? So it is basically the partial derivative of Lagrangian function with respect to a given parameter. When we talk about given parameter in the indirect utility function, the given parameters here, we have price and also income. So Roy's identity uses envelope theorem, and envelope theorem says the partial derivative of Lagrangian function with respect to a given parameter that are, prices and also income is equal to the total derivative of our objective. Okay, when we evaluate it at variable optimal points. All right. Now, don't worry if you still don't understand this. I'll explain to you more in a bit. Okay, so this envelope theorem is very important to explain Roy's identity. Why? Because it helps us to analyze a closely linked economic environment where variables are described in this environment in this way. Okay, so how to explain this concept? So the first thing here, let me show you one by one. I'll use one example of direct utility function, and then from there I come up with Marshallian demand function. And from there I'll use envelope theorem to come up with Roy's identity, and then after that, with Roy's identity, then we can show that we can get Marshallian demand function. Okay, we can recover actually the demand function from the indirect utility function. Now here, so that means if you know the indirect utility function, then you can always recover the demand functions. So this is what Roy's identity is trying to say. So again, like I said just now, we can always use envelope theorem to show Roy's identity. So let's use one example here. Let's say we have, I start from the beginning, yeah? So let's say we have this direct utility function, u equals to x, y. Okay, it's a linear, simple one. Subject to this constraint, x times px plus y times py less or equal to m. Right? Now, from here, if you can recall back in the first video, in order to find the optimal level of x and also the optimal level of y that can satisfy you, then I need to do what we call consumer optimization, isn't it? First, as usual, construct a Lagrangian function. So Lagrangian function here is xy plus lambda in bracket m minus xpx minus y py, isn't it? So this is Lagrangian function. So as usual, we need to find the first order condition because this is the optimization problem of utility. Then differentiate lambda with Lagrangian function with respect to x. We get something like this, y minus lambda px equals to 0 in it. We do the same for y. Then we get x minus lambda py equals to 0. This is 1, this is 2. And then we do the same for the last one, this, which is lambda. And then we have m minus xpx minus y py equals to 0. We call this 3. Alright. Now, if you have 1 here, then you can have this. We can rewrite it this way. Y equals to lambda px in it. And then from here, we can also have lambda equals to y over px. So we can also do the same for 2. This is what I mean. then we can have x here equals to lambda py. Then this implies lambda equals to x over py in it. Okay, so let's call this one 1a. Let's call this one 2a. So we can see clearly that 1a equals to 2a, isn't it? Basic, yeah? So I bring it here, yeah? So when 1a equals to 2a, then this implies y over px equals to x over py in it. So from here we can have y equals to px over py times x. Now I call this one 3. Also from here we can also have x equals to py over px times y. So I call this one 4. If you see here, the main point is to find x star and y star, the optimal level of good x and good y that can yield the highest level of satisfaction, that is u. Okay, so what you need to do is you need to find this one. This is unfinished work. So you should have 3 and 4 insert back into this budget constraint to find x star and y. So these things I won't show you how to do it one by one because this is just a simple calculus which you already did in your high school or secondary school. So here, finally, after you do some, arithmetic calculation, the calculus, then you should get x star equals to m over 2px and y star equals to m over 2py. So I call this one 5 and then I call this one 6. Okay, equation 5, equation 6. If you see these two, like I said previously, these are the Marshallian demand for x and y respectively. Okay, right. Now, I haven't explained to you up to this point how does Roy's identity look like and how envelope theorem can help you to show Roy's identity. Now, from here we can construct what we call indirect utility function. We know that the direct utility function is u equals to x times y. So in order to obtain indirect utility function, you just need to substitute x star and y star. So here, okay, when we have the indirect utility function, then we call it v, isn't it? Now you look here one by one. So m over 2px times m over 2py. And if we simplify it further, then we have m squared over 4px py. So this is our indirect utility function. So as you can see here, so can you see that, okay, both, both good x and y, variable x and y are not, appearing in the indirect utility function. What appear here are price of x and also price of y as well as income. So you can see that the indirect utility function is actually a function of two parameters. The first one is income and the second one is prices. In particular, prices of good x and also good y. But if you see the direct utility function, if I rewrite it again here, because I don't want to mix up with this here, because this is at the optimal level. The direct utility function is a function of variable good and y. But the indirect utility function is not directly a function of good x and y, but it is a function of prices and also income, the two parameters which are given. not determined by the consumer. This one you determine it through the process here. You determine it. But this one, income and also prices are exogenously given in the system. But you can see that income and prices here are the factors that can affect the indirect utility function. I hope up to this point it is clear. So this kind of exercise is actually the revision of what you have seen in video 1. Now, so in this case, is equal to U star, yeah? Okay, direct utility function at the optimal level is actually the indirect utility function. Now, the next bit is very important because the next bit we are going to use it for, Roy's identity. So we want to have envelope theorem here to help us using Roy's identity so that we can recover Marshallian demand. Okay? So envelope theorem says what? You have to listen to this very carefully. Actually, when we talk about envelope theorems, there are two parts of it. Let's go back to this slide, yeah? You can see this is the line that divide the numerator and also the denominator of Roy's identity. So the first one here is actually the partial derivative of indirect utility function with respect to price of a good I. And then the second one here is the partial derivative of the indirect utility function with respect to income. So envelope theorems for this particular example, which is utility function, has two different parts. The first one is this, and the second one is this. Right. Now, let me show you the process one by one. So when we talk about envelope theorem here, like I said just now, okay, we have two parts. The first one is this, and the second one is this. Okay. Alright, the envelope theorem says that if we differentiate the indirect utility function with respect to price of good I, then it is actually the same as the way we differentiate the Lagrangian function with respect to price of good I, parameter. Okay. And the same goes to, the indirect utility function in the second bit here. If we differentiate the indirect utility function partially with respect to income, that is just the same as differentiating the Lagrangian function with respect to income. And if you can't remember what is the Lagrangian function, the Lagrangian function is actually this. For this example, yeah? Xy plus lambda m minus xpx minus y times py. Let me fix it here. Right. So py. Okay, so this is the Lagrangian function. So if you see this Lagrangian function here, which we already saw it earlier, which is this, yeah? Then if we differentiate it with respect to, let's say pi here, I'm talking about good s because we have two goods of I. So I here is xy because we only consider two goods in this case. So let's say I differentiate, Lagrangian function with respect to px instead. So let me make it more specific. Instead of writing pi, I write it px. Px, yeah. So what I'm trying to say is that we need to differentiate the Lagrangian function with respect to the price of px. Then what do we get here is actually minus lambda x, isn't it? Right? Okay. And remember, when we differentiate indirect utility function with respect to px, that means we get minus lambda x. And this indirect utility function is at the optimal level, remember? Therefore, this one, x here is x star. Alright? Okay. Now, if you look at the second bit here, we differentiate the indirect utility function with respect to income is also the same as differentiating Lagrangian function with respect to income. And you're going to say that the answer here is differentiate it with respect to income, then you have lambda. This is basic differentiation that you have learned in the high school and also the first degree. Yeah? So I won't teach you one by one about how to differentiate. If you forget, you have to go through all the basic maths that you have learned at the undergraduate level. There are a lot of examples that you can refer to from YouTube if you're lazy to read books. All right, now, can you see why the differentiation of indirect utility function with respect to price of goods or income here is just the same as differentiating Lagrangian function with respect to any parameters such as price or income here? Because the Lagrangian function here is basically comes from the maximization problems of utility subject to what? Subject to budget constraint, isn't it? So subject to P times PI times XI, PI times XI, and that's equal to income, isn't it? So that's why the process is just the same. And then after that, when you take the ratio between these two, okay, when you take the ratio, you're going to see X star only. So that's how we recover Marshalling demand function if we know the indirect utility function given to us. All right. Now, so here, let's go back to this particular example. So we have this, and recall back, we did some, optimization from the direct utility function. We know that lambda is actually what? Lambda is actually 2a, and also we have here 1a, remember? Okay, so let me go back to this slide. So if we have lambda equals to ypx, isn't it? And then we have also, y star equals to m to py, isn't it? Therefore, we can have lambda equals to here, if we try to, rewrite it, m equals to 2 px py in it. Okay. So that means lambda here is actually this. Okay. So m over 2 px py. Can you see? Because we substituted back here. Alright. So I call this one expression 9. I did forget to write some number here. So let's say this one, 5 and 6. And then this one is actually 7. Okay. And then actually this is actually 8, yeah, not 9. Let me erase it. 8. And then this one is, let's say, we have 9 here. Okay. Now, we have done the indirect utility function with respect to income. We can do for this also. Okay. So we get this. All right. Now, so from here, so let me write it here again. Okay. So delta over delta px equals to delta L over delta px minus lambda x star. Then this one gives us minus m 2px py times x star. Alright, now if we take the ratio of this and also this, then we get x star after the sign change, yeah? because you still see the minus sign here. So here, specifically, what is x star? Let's use the example again. Okay, so we know that the indirect utility function that we obtained earlier is u star equals to v as a function of p and y equal p and m, yeah, not y. P and m equals to m squared over 4px py. Okay. If we take the partial derivative of indirect utility function with respect to price of x, then what we get here will be minus m square over 4 px square py in it. Yeah. So this is the first bit. Now, secondly, if we take the partial derivative of indirect utility function with respect to m, yeah, what do we get? We get m over 2px py. How do you get this? Make sure you know how to do the partial derivative that you have learned in your high school and also your first degree. So how to come up with Roy's identity here? It's very simple. You just take the ratio between these two, then, put the minus sign. Okay, so Roy's identity is minus delta u over delta px for good x over delta u star. I put u star because u star equals to v, yeah? And delta m equals to, in this case, don't forget the minus sign. And then we have minus again because this one is the answer that has minus, okay, m squared over 4px squared py over m over 2px py. So when you solve it, you're going to get this m over 2px py. So what is this? This is the x star. If you go back to our previous, work for utility maximizing problem, okay, if you solve it like this from the direct utility function, then you get the Marshallian demand for good x, which is m over 2 px. Isn't it the same? So here, class, this is this. I think py cancel out, eh? So we shouldn't see py here. This is the correction. So isn't it the same? So here, the main idea about Roy's identity is that if we use envelope theorem, we don't have to go through a very detailed, process of getting back or recovering back the Marshallian demand for any good if we know indirect utility function. Yeah. And one thing that I want to emphasize here from the beginning of the process, let me recall back. You are given the direct utility function, which is u equals to x times y. So we have two goods. In this case, I are basically x and also y only, the two good case. Subject to this budget constraint, okay, what we want to find is the optimal level of x and y that this individual consumer consume in order to maximize his own utility given the constraint. So to do this, we need to perform Lagrangian method, isn't it? This is a typical thing. And then you get the first order condition and whatnot. And then you reach to the equilibrium. We found the Marshallian demand for x and y respectively. And then we substitute these two back into the direct utility function to obtain the optimal level of utility function, which is the indirect utility function given by 7. Now, if let's say instead of given direct utility function, you are given the indirect utility function, How do you find X star and Y star? Because here X star and Y star already mixed up. Do you get what I mean? Do you need to go back reverse like this process, Lagrangian and whatnot? No. But the process of going back, reverting here, has something to do with what we call envelope theorem. I did mention to you, let me use different color of pen. I did mention to you just now, the Roy's identity that you saw, let's go back to this slide, consists of two different parts. The first part is this, the second part is this. The first part is the partial derivative of the indirect utility function with respect to the price of good I. If we want to find Marshallian demand function of good I, then you differentiate it with respect to the price of good I. Okay? In our example case, is good X. We have two goods, X and Y. We want to get back the Marshallian demand function for good X. And the second bit here, or the second part here, is differentiating the indirect utility function with respect to income, M. Okay, so we have two bits here. Now, the first bit and the second bit here, we want to revert back to get this. The process going through has one kind of theorem that is utilized, and that theorem is envelope theorem. Alright? Now, in envelope theorem, it says what? It says, if you go back to this is the first part of Roy's identity in it. The first part of Roy's identity is the differentiation of indirect utility function with respect to price. It's just the same as differentiating the Lagrangian function of the direct utility function with respect to price of good X. That's what envelope theorem says. And the answer is always this. Always and always for good X. If it is Y, then you put Y here. As simple as that. So rather than going through from here to here, in order to get this, then you know that this one is actually this. Jump. You get what I mean here? But the process from here to here, the explanation is the envelope theorem here. Okay? So same thing for the second bit here. The differentiation, the partial differentiation of indirect utility function with respect to income is actually can be done by partially differentiating Lagrangian function with respect to income. Okay, if you recall back, this is the Lagrangian function, then the answer is always lambda, always and always and always. So if we take the ratio between 1 and 2, then lambda cancel out each other. Then what you get is that minus X star. The minus sign, you bring it to the left, then you get something like this. Now let me clean up this. This has become a mess already. So you can see, remember, so we have dv over dpi equals to minus lambda X star, and then we have dv over dm equals to lambda. So you take the ratio, these two, then it becomes what? dv over dpi over dv over dm equals to minus lambda X star over lambda, cancel. You have minus sign, you bring it here. So that's why you see minus sign here after the sign change. Yes, that's why we have the term here after the sign change. Okay, after a sign change here, then here we have, let's go back to this. So lambda cancel out each other. Then what you can say is that you can recover back the Marshallian demand for good X. Alright, so the process here going through what we call envelope theorem. Alright, now, because we already know how does Roy's identity look like, so if you have indirect utility function like this, how do you get X star back from the indirect utility function? You just need to apply Roy's identity, as simple as that. So instead of going through one by one, because you don't even know how does the direct utility function look like, isn't it? If you know, then you won't go through this. Then you just take the ratio like this, do the differentiation as well, then you can see that this is the answer for the Marshall unit demand for good X. Why don't you try for good Y? From here, try to get, use Roy's identity to get, back the Marshall unit demand function for good Y. So I hope this is clear for you. So these are all about the properties of indirect utility function, including Roy's identity. It should satisfy Roy's identity. Now we move to the expenditure function. So here is a bit different from the utility function, direct and indirect utility function. When we talk about expenditure function, it is derived from a different kind of optimization problem. Why? Because instead of asking what is the maximum level, we ask what is the minimum level of money expenditure the consumer must make to achieve a given level of utility. Now, so in a formal way, it can be written as this. Expenditure function as a function of price and also utility is equals to minimizing total expenditure, which is this, subject to utility of bundle X, okay, and such that the set of bundle is positive or non-negative real number in n dimension. All right. Now, let's say we have a set of attainable utility levels, which is given by this expression. This expression says that U, capital U, is a set of many attainable utility levels, and it consists of utility levels of bundle X such that X is non-negative, a real number in the n dimension of goods or commodities. So in this case, if this is the sets of utility levels which is attainable means you can attain, you can get it within the budget constraint. Therefore, the domain of your expenditure is actually given by this, in which it is a much positive a real number, okay, not include zero in the n dimension here of goods, and then at the same time with the utility level which is attainable. Now, when we talk about expenditure function here, we want to minimize total expenditure subject to utility, okay? An expenditure function is a function of price and also utility, as you can see here. Then when we try to solve it, then the solution for this, okay, let's say good here, is what we call x h function of P and U. Okay, there is a name for this, and this name is what we call Hicksian demand function. If you can recall back direct utility function, when you solve it, maximizing direct utility function subject to, Px less or equal to M, the budget constraint, then the results here, X is what we call Marshallian demand function, isn't it? Y is what we call Marshallian demand function, but this one for expenditure, when we get the optimal level of bundle, we call it Hicksian demand. Alright, now the idea is like this. Imagine that we have a process where the consumer's income is changed. So income can change, okay, to compensate him for changes in price such that he can achieve exactly the same utility as level as before. So here you have income, okay, and then you want to achieve the same level of utility, the same level of happiness, the same level of satisfaction as before. Let's say previously when you consume X and Y, okay, the utility is equivalent to 10. Now let's say with this amount of, X and Y, let's say X here could be 5X, 10Y, so whatever number, this bundle, Okay, suddenly there's a change in income. Okay, you change the income. Obviously, if you want to maintain the same utility, you have to change, the amount of X and Y you want to consume, so that it compensate, you know, the change in income and can maintain the same level of utility. All right. Now, so that means the optimal level of quantities of X and Y goods or commodities here can change because income changes, but we want to maintain the same utility. But for the expenditure function, what we want to find is what happens to, expenditure function as a function of price and utility. Then, like I said just now, the results is this. It is Hessian demand function. It is a function of price and utility. Here for Marshallian demand function is a function of price and income, isn't it? But this one, Hessian demand function, it is a function of price and also utility. So X here is the vector of this demand. So it can consist of XH here can consist of 1, 2, 3, 4, 5. Yeah. So this is what it means. Alright. Now there are some properties of this expenditure function, and this can be summarized in theorem 5. Let's look at theorem 5. If the direct utility function is continuous, ux is continuous and strictly increasing on non-negative real number with n types of goods, then expenditure function as a function of price and also utility is actually having these properties, which are more or less 7 properties. The first one is 0, when utility takes on the lowest level of utility in U. Number 2, continuous on its domain. Okay. And number 3, for all price much greater than 0, that means prices are positive, strictly increasing and unbounded above in U or utility. Number 4, strictly increasing in prices. Number 5, homogeneous of degree 1 in prices. Remember, P here, when I write it P, it means price vectors. And 6, concave in prices. And 7, if direct utility function is strictly quasi-concave, we have Shepard's lemma. And Shepard's lemma says what? Expenditure function is differentiable in prices at certain price, let's call it P0 or P0, at certain utility level U0, with P0 here is much greater than 0, non-zero number, and it has to be positive. Therefore, Shepard's lemma says if we take differentiation, partial differentiation of expenditure function with respect to price of good I, then we can get the Hessian demand function. Okay, so I here is good 1, good 2 until good n. So with n number of products or commodities. So let's look at each of the theorem one by one here. Some of them I'll explain, some of them I won't explain to you because it's just a statement that if you can understand the theorem for direct utility function, then you can also understand the theorem for expenditure function. So let's crack on. The first property is that the expenditure function, which is E as a function of prices and also utility, is 0 when utility takes on the lowest level of utility in the set of utility levels. So here, what does it mean? You look here, the lowest level of utility in the set of many utilities is actually what? It's actually when you don't consume any bundles. So when you don't consume any bundle, Ux here is actually U0, isn't it? And remember, the properties of the direct utility function is strictly increasing. Okay, so when x here is equivalent to 0, we don't consume anything. So it doesn't require any expenditure to spend on it, isn't it? So expenditure itself is 0. And therefore, when expenditure is 0, then expenditure function itself, okay, is 0, isn't it? Okay, so that's the first property. Now, the second property is continuous on its domain. And what does it mean by this? If you can recall back, the utility function is also continuous in its domain, isn't it? The main thing about continuity of expenditure function or utility function is that it allows us mathematically to differentiate the function. Therefore, it has something to do with differentiability concept. Now, number 3, for all price which is much greater than 0, it is strictly increasing and unbounded above in U. Okay, so what does it mean here? Strictly increasing and unbounded above in U. The expenditure here is very simple. For if the price is positive, so of course the expenditure is also positive when you want to consume, isn't it? And when the prices is even more, okay, or strictly increasing, okay, the minimum level of expenditure needed to maintain the same utility level also increase, isn't it? That's logic. All right. And number 4, strictly increasing in price has something to do with the explanation that I said to you just now. But in order to prove it formally using mathematics, this one can be also proven together with a 7, that is Shepherd's lemma condition. Okay, I'll show you this one later once we move to 7. Now number 5 is homogeneous of degree of 1 in prices. P is the prices vector, yeah? So when we say that it is homogeneous of degree of 1 in prices, technically speaking, it means when prices double, then the minimum expenditure that we need to perform to obtain the same targeted utility level or to get the same level of utility must double as well. So it means the prices and also expenditures in this case has the same ratio in terms of increase. So intuitively that is, if the prices increases and you want to maintain the same level of utility satisfaction, okay, so of course you have to spend more. When you spend more, spend by the same proportion of prices, isn't it? That is for your expenditure. So you need to spend the same increment, the same proportion of increase in your expenditure when the prices increase proportionately. Now, if you look at the next one, it says concave in prices or concave in P. So expenditure function is concave in P. So how do we explain this? I have explained most of the properties of expenditure functions. Some of them I explain it with proofs. Some of them I didn't explain with proof because some of them I believe if you can understand utility functions properties, and I did show to you some of the proofs of utility functions, then you should be able to prove some of the points for expenditure functions. Now, how to prove number 6 here? Okay, property number 6 says that it is concave in prices. So expenditure function will be concave in prices if this condition holds. And this condition says expenditure evaluated at price equals to P double prime with a given utility U is greater or equal to some weight, call it alpha, multiplied by expenditure evaluated at price equivalent to P for a given utility, the same utility U, this utility here is the same as utility level here, yeah, plus 1 minus weight, which is alpha, times expenditure evaluated at price equivalent to P prime with the same level of utility. So how do we explain the concavity in prices of expenditure function here? So we have three different prices, as you can see in these combinations of conditions. So we have P, we have P prime, and we have P double prime. And P double prime here is a linear combination of P and P prime with a given weight, call it alpha. Alright, so P double prime is actually a linear combination of P and P prime. How do we combine this to become a linear combination? By using the weight alpha. It is equals to alpha P plus 1 minus alpha times P prime. So that is P double prime. So we have three different prices here. And at the same time, alpha here is the weight, must be between 0 and 1. So just imagine if alpha here is 0.5, so the weight given to P is half, the weight given to P prime is half to get P double prime. But if alpha here is 0.3, the weight given to P is less than the weight given to P prime to get P double prime, isn't it? Alright, now how do we explain this graphically, concavity concept for expenditure function? So let's look at the drawing. Let's say graphically our expenditure function looks like this. So we have vertical and also horizontal axis. On the horizontal axis we have prices, and on the vertical axis we have expenditure, and concavity of expenditure may look like this. Okay. So this is expenditure as a function of price and also given utility. Now here, in the form of graph, let's say I want to locate price P. Let's say price P is here. So the associated expenditure when price is at P is this, E, P, and given utility. And I have another price, call it P prime. Therefore, the associated expenditure is here. And this one is E, P prime as a function of P prime and also a given utility. And I have the third price, which is a linear combination of P and P prime. So it should be between P and P prime in it. So let's say it is somewhere here. So I call it P prime, a double prime. Therefore, the associated expenditure is this. So let's say E, P double, function of P double prime and a given utility. Let's call this point E. Now, when we have P double prime, like I said just now, it is a linear combination of price P and also P prime. So in the form of graph, a linear combination, P is here, P double prime is here. Let me use different color, let's say red. So if I join P and P prime using one color red, then I get a very straight line. This is a linear combination of P and P prime. Okay, a linear combination. So price here, P prime could be somewhere here. Alright, now, so here, P double prime, again I rewrite it. It's actually a linear combination between P and P prime. Okay. Now, the definition of concavity, like I said just now, let me rewrite it again, is this. Greater than alpha E PU plus 1 minus alpha E P prime U, in it. So that means the expenditure at P double prime is greater or equal to the combination of expenditure at P and also P prime level. Okay, in this graph, you can see clearly. All right, now how to prove this? So to prove this, we need to use mathematics. So this is the proof. Listen to it carefully. Let's say we have P double prime. So the expenditure evaluated at P double prime is given by this with a given utility. And this is actually price P double prime times this. All right. Now, what does it mean by this? This is actually the cost of optimal and the cheapest bundle. Call it Hexian demand. Yeah? This is the cheapest bundle. XH here. XH is a function of price P double prime and a given utility. And then this is the price. Price times Hexian demand is total cost of an individual consumer, isn't it? So it is the cost of optimal and the cheapest bundle, which is Hexian demand, that we can get when price is at P double prime for a given utility. Now, like I said just now, because P double prime is a linear combination of P and also P prime, then what does it mean? This one is actually equals to this. Alpha P, Hexian demand, this plus 1 minus alpha P prime, Hexian demand at P double prime. Now, here we can see clearly bundle XH here is optimal if it is for the price of P double prime, but it is not optimal for the price of P and also P prime. If you look here, I use different pen. Look at this. Okay. This is what? This is actually the cost of the bundle for optimal good XH. However, it is evaluated at different price. What is that price? It is evaluated at P instead of P double prime. But the best and the optimal and the cheapest is when it is at P double prime, isn't it? And what about this? Look at this. This is the cost of bundle for the optimal good, which is XH, but evaluated at P prime price, not P double prime. So here, XH is actually optimal for P double prime, but not for the price of P and also P prime. So that means this bit, let me use different color. This bit is actually more or equal to expenditure at P prime, at P, sorry, yeah? And this bit is actually more than E expenditure evaluated at P prime for a given utility, isn't it? Okay. Now, the whole thing here, after equal sign, therefore, is actually greater or equal to what? Greater or equal to this. Isn't it? Okay, because I just take alpha, bring it here, and then I take this, bring it here, and then I take 1 minus alpha, bring it here, plus, stay the same, and then I take this one here. So because more or equal to, then the whole thing more or equal to. You get what I mean here? Now, in the form of graph, where it is? So, you see here, E expenditure evaluated at price double prime, P double prime, with a given utility is at point A. is bigger or greater or equal to than the linear combination of expenditure of P and P prime. So the linear combination should be somewhere here, isn't it? Between this red line. So in this case, if alpha is, let's say, 0.5, then the whole thing here, which is after greater sign, I'm talking about this, yeah? Where does it situated? Could be here, halfway between P and P prime. If I say alpha is 0.5, but if I say alpha instead of 0.5, probably 0.3, so that means the weight for P is less than the weight for P prime, so could be here. Okay, so let's call this point B, let's call this point C. So still point B and C is below A. That means expenditure here is more equal to B and C. So that is the concavity proven. Okay, so here I can put small letter, small square here. What's so important about the results of concavity of expenditure function here? It has a very significant rule, because later it's going to show the negative semi-definiteness of Slutsky metric that you need to learn later. All right, so that's the proof for concavity in prices of expenditure function. But then conceptually, this is the proof, and conceptually I did explain to you a little bit. Conceptually, for your understanding, other than mathematics, yeah. So what does it mean by concave in prices P for expenditure function? Conceptually speaking, when we say concave in prices for expenditure function, we can show it in the form of graph. And this is for your understanding, yeah, so that you can get the economic intuition behind all of these, properties. So we have expenditure function as a function of price and also utility. And we say that it is concave in prices. So what happens here is that if price increases, then the minimum expenditure required to obtain the same level of utility will increase by smaller rate. That's what it means by concavity. Expenditure increases at smaller rate or at decreasing rate. So if we put it in the form of graph, you already knew that the expenditure function looks like this. So if we have prices here and we have expenditure here, it is concave like this. So E as a function of prices and also utility, given utility. So if price increases for the first commodity, then intuitively, the consumer simply substitute, let's say this one is price P1 increases for good one or X1, then simply the consumer will substitute X1 by less expensive commodity, call it X2. And we have substitution effect here. So as a result, when the consumer can substitute some amount here from X1 to X2, so of course the expenditure here becomes, increase not at increasing rate but smaller rate. Okay, so that's why it leads to concavity, because you can easily substitute the product with a less expensive item. But what if this concavity doesn't happen? So let's say price of good one, X1 increases, then because X1 doesn't have any substitute, so the demand for X1 would remain the same when no substitute. And in this case, what happens to the expenditure function? So if we have prices here and expenditure here, then the expenditure function becomes a linear line, isn't it? So expenditure increases linearly with the increase in price. Okay, so the rate is the same because you don't substitute it. So for instance, usually you consume X1 equivalent to 5. Okay, the initial price is equivalent to 10. Now price increases to, let's say, 20 with the same demand, 5. So what's your expenditure here? Expenditure here becomes 100, this 150. So it increases linearly. Okay, if I have another one here, increase even further, then the change here 50, the change here should be 50 as well per, per quantity, for instance. Okay, expenditure per quantity. Okay, additional expenditure. So here, so let's say we pick one point here. This one is concave at this point. If I draw a straight line like this, if let's say it's not concave, then this straight line is just an imaginary line. So this imaginary line is what we call pseudo expenditure line, which doesn't really exist, we just imagine. So that's the difference between concavity and also linear expenditure. As you increase even further, let's say you move from point A to point B, for instance, you can see expenditure here, the line becomes flatter and flatter, isn't it? The tangent line becomes flatter and flatter because of the substitution effect. When the price of one good increases, simply consumers substitute to another relatively cheaper price. But if let's say your demand doesn't change, then you have straight line like this, pseudo expenditure line. Okay, so I hope this is clear for you. We want to prove the last properties of expenditure function, that is property number 7. So property number 7 says that if the indirect utility function, which is ux, is strictly quasi-concave, then we can have Shepherd's lemma, in which expenditure function is actually differentiable in prices at, let's say, certain price P0 or P0 and utility U0, such that P0 is much greater than 0 or positive, and therefore we can have this Shepherd lemma here. That is, if we differentiate the expenditure function with respect to price of one good, let's say good I, what we get here is that the Hessian demand of the Hessian demand of good I itself, such that I is good 1, good 2, or good 3, or until good n. So this is what we want to prove here, and this is the simple proof. However, before I prove property number 7 here, I want to show you this thing. If you can recall back, when we talk about expenditure function, let me erase the mess here so that you can see. The expenditure function here, we are asking ourselves what's the minimum level of money expenditure that we as consumers must make to achieve a given level of utility. And then the expenditure function is defined as this. Instead of maximizing, we want to minimize expenditure, isn't it? So minimize total expenditure here, subject to the utility, okay, of one bundle, call it bundle X. And bundle X here consists of a number of good 1, a number of good 2, a number of good 3, until a number of good n. Okay, so how do we get the answer here? When you do the first order condition as usual, like the way we did for utility maximizing problem, in the utility maximizing problem, what we get is Marshallian demand function. But here, what we will get is what we call Hessian demand function. So how do we do it? I'm going to show you this first, because once you get the answer for this, then we can use some bit of it to prove property number 7 of expenditure function. So let's begin. We have expenditure function, okay, which is maximizing total expenditure subject to utility. Okay. What we want to get here is the Hessian demand function. And this Hessian demand function, later when you get the answer, you'll see it is a function of prices and also utility. So if prices changes here for a given utility, okay, what happens to the Hessian demand function here? Now you look here, P here is the vector of prices. So P here consists of P1, P2, price for good 2, price for good 3, until price for good n. And X here is the vector or the bundle of, consisting good 1, good 2, good 3, until good n. So remember that. Yeah, so whenever I write P and X only, it's basically collection of prices and also collections of good in a bundle respectively. So we have here Xn. Alright. Now, so how to solve this so that we can find Hessian demand function vector here. So in the vector here, we're going to have x1h, x2h until xnh. And all of this xh is a function of prices and also a given utility. So how to solve it? As usual, like the same way we solve for utility function, the direct utility function that you saw in the first video. So we need to perform, or we need to construct what we call Lagrangian function. So construct a Lagrangian function. So I call it L. L is actually equivalent to Px plus, instead of using lambda, because I use lambda for utility so that we can differentiate it, yeah? So I use, let's say, C, great letter C, and then in bracket here, U minus Ux, for instance. Okay, U minus Ux, for instance. So how do we do it? So we need to find FOC, first order condition. Remember, we want to minimize it instead of maximize. This is an error. Minimize. Nobody wants to maximize expenditure. Everybody wants to make it as cheapest as they can so that they can save a lot of money. That's the intuition behind it, instead of putting maximize. So let's say this is a cost function. So you want to minimize here. You don't want to pay cost higher here, isn't it? You want it to be here. So when it is minimized, the minimum possible is this point. So when you put a line and call it tangent line, mathematically speaking, at this minimum point, the line is flat. So that means when you calculate the slope is equals to 0. So the slope equals to 0 here. How do we show it in mathematics? So Lagrangian function here, you need to differentiate it with the price of good and equate it to 0 so that the slope here is 0. Okay? So the slope differentiation of slope here is delta lambda over delta p. Okay, all of the p we need to do, and also the last one with a c as well. So let's do the FOC of first order condition. So if you're talking about good one, then differentiate Lagrangian function with respect to good one. Then what you get here is, remember, p consists of p1, p2, p3. Then you have this p1. Because if you see this one, it looks like this, yeah? Let me show you if you still don't understand. Before I show you FOC, because some students still don't get this Lagrangian function. So if I write in detail the Lagrangian function, it looks like this, yeah? L equals to P1x1 plus P2x2 plus, until the last one, Pnxn plus C u minus u as a function of x1, x2 until xn. Okay? So from here, it becomes easier if you want to differentiate it. So we need to find first order condition of this Lagrangian function to help us to find Hessian demand for good 1, good 2 until good n. So what I'm doing here is not using number, but I use generate function to do this. So here, delta L over delta x1, what you're going to get here is, you see this? You see x1 is here, isn't it? So this and this you need to differentiate. So what you get here when you differentiate, simply P1. Alright? And then when you differentiate this, then you see lambda constant is attached to this. This is basic math. So you have this, and then delta U of x1, x2 until xn over delta x1 in it. And then equate it to 0 because this one is a slope, But if you equate it to 0, then you can have flat here. That means minimum point of expenditure. Now, instead of writing like this long, like this, so I use one letter, which is x, to represent the vector. That's why you have du dx. Okay, so let me rewrite it again nicely. Then we have something like this. So you have C delta ux over delta x1 equals to 0. So you can do the same thing for x2. So you're going to get this. C delta ux over delta x2 equals to 0. Until you do more and more here, until you get dl over dxn equal to pn minus c delta ux over delta xn equals to 0. Alright? And then after that, solve it as usual, like the way you did it for the direct utility function to get Marshallian demand function. Then, you can, of course, get the Hessian demand function for good 1 equals to what? And then Hessian demand function for good 2 equals to what? Until Hessian demand function for good n equals to what? And if you see all of this, the Hessian demand function, so I write in the form of vector so that I don't have to write like this. The Hessian demand function is actually the function of a vector of prices, P1, P2 until Pn, and also a given utility. So that's how you solve it. This is just a generic form. You can see examples from, textbook, and also the simplest way is to look at the YouTube. If I give you, let's say, expenditure function, specific one. All right? So I hope you can do exercise on your own. Now, here, don't forget, not only this, before you can find Hessian demand function like this, you also need to differentiate the Lagrangian function with respect to C. When you differentiate Lagrangian function with respect to C, this is what I mean. Because otherwise you forget to differentiate this. The same thing like the way you did for utility. And what you get is that u minus ux equals to 0. Then this one implies u equals to ux. So what does it mean by u equals to ux here? Then it means this individual consumer constraint, which is utility, is a constraint to the expenditure, isn't it? It's constraint is binding. And when it is binding, the C value here will be greater than 0. If it is equal to 0, you can never solve this mathematics. I mean, just imagine if this is 0. When this is 0, no matter what number multiply by this, it's always 0. Then Pn equals to 0. You get what I mean here? When Pn equal to 0 or P1 equal to 0, can you always solve for Hessian demand, H1, 2 until n? You can't. So that's why we need to have this kind of, differentiation for Lagrangian multiplier. In this case, Lagrangian multiplier, I put C. You can put lambda as well, but I just want to differentiate it from the multiplier of direct utility that we did in the previous video. All right. So in this case, at the same time, if we have this, and this is what we call individual's constraint in the form of utility for minimizing expenditure is binding, then we can always have this, multiplier, Lagrangian multiplier is positive. So when Lagrangian multiplier is positive, it's easy for us, mathematically speaking, to find the Hessian demand function and whatnot. Okay, just imagine if this one is not positive, it is equal to 0, then this one is not binding. When this one is not binding, mathematically speaking, the first order condition that we are doing here is useless because you can never find the answer. Okay, so that's why we need this kind of condition. Now, we are done with this. Okay, so we need to go back to our objective. Our objective is to prove the property of expenditure functions in number 7, in which, let me go back to the slide here. if the direct utility function is strictly quasi-concave, we can have Shepard lemma with this, condition such that Shepard lemma says, if we differentiate expenditure function with respect to the price of good I, then we can get back, we can get the Hessian demand function of good I. Okay, so this is the same like the way we did for the indirect utility function previously using envelope theorem. So the Shepard lemma here, we can also use envelope theorem to prove it. So we are going to the process of proving. Now, if you look at this process of proving here, this has been simplified in this way, in this manner. But I'm going to show you in detail so that you understand why it becomes like this. Because if you're very good in mathematics, I would leave it just like this. But since we are struggling with mathematics, I'll show you the proof one by one here. Now, let's do it. Let me rewrite again the expenditure function here. The expenditure function here is a function of vector prices and also a given utility. And this one, everybody knows that when we talk about the expenditure function, we have something like this. It is actually the total expenditure prices times goods, okay, quantity of goods. Remember, P is actually P1, P2, P3, until the last one, Pn. If you just only have 3 different goods, so you stop at P3 in it. And X here is a bundle or a vector of goods, combination of good, X1, X2, until Xn. So if I were to make it in detail, then this expenditure function is actually equals to what? P1x1 plus P2x2 plus P3x3 plus until the last one, Pnxn. So in order to for us to show that the Shepard lemma here exists, we need to differentiate the expenditure function with respect to price. Okay, so when we differentiate it with respect to price, we can get the Hessian demand function. So let's say, given this, okay, so here, if I put, if I put I here refers to 1, 2, until n. All right. So let's say I want to differentiate, I want to get back the Hessian demand function for good 1, for instance, or good I. Let's say good I here refers to good 1. So the rest here refers to, J. Okay. Now, so I need to differentiate the expenditure function with respect to good 1 or good good 1. Yeah, we start with good 1. Then after that, I make it general. All right. So here is going to be, you look here. If I differentiate this with respect to good 1, what do I get? P1, isn't it? Then that's it. Okay. But remember, when we try to differentiate expenditure function with respect to price 1 here, this expenditure function here is is a situation where the expenditure has been minimized. So when it has been minimized, so every good here, good 1, good 2, good 3 until good n are all actually at the optimal level. Okay, at the optimal level. So in this case, because it is at the optimal level, let me erase this mess here. Then I put H here, Hexian. But I don't know X1 H equals to what? I don't know. So that's why I want to find it using this method, Shepard lemma. Okay. So here, H until the last one. All right. And we know that once we find the Hessian demand for any good, it is a function of price and utility, isn't it? Remember, I did mention to you just now, if you go back to the previous slide, when you solve the first order condition of this, then what you get is what we call Hessian demand as a function of prices and utility. Okay, so this is Hessian demand functions, or also known as compensated. Okay, so if we have x1h, x2h, and whatnot, then we have a vector of Hessian demand function in it. Okay, now let's go back to this because our purpose is to prove the property number 7, which is the existence of Shepard lemma condition that gives us Hessian demand function. All right, so here let's go back to this differentiation. Differentiate expenditure function with respect to good one because we want to find Hessian demand function of good one. Okay, can it exist or not? All right, so and then the rest here, P2 is a constant, but we need to differentiate, x2h here with respect to P1y because x2h also it depends on the vector prices. When it depends on the vector prices, it's not only P2, but it consists P1, P2, P3. So that's why you still need to differentiate it with P1 because Hessian demand function for good 2 is a function of vector of prices, not just P2. All right. Now, continue here. I need more space, that's why I need to erase this. Now, plus P3 delta x3h over delta P1 plus until the last one Pn delta x and h over delta P1. All right. Oh, I made mistake here. Then I realized something is wrong. Shouldn't be P1 when you differentiate it with respect to P1. P1 is the variable, x1h is the constant, so x1h, otherwise you can never get the Hessian demand function. Anyway, so here, then, if I simplify it, x1h, all of these, okay, plus something that I missed also here. Remember, like I said to you just now, P1, x1. P1 does not depend on anything, but x h1 also depend on vector of prices and u, isn't it? Then I also need to have P1 delta x1h over delta P1. You get what I mean here? I hope you can understand, yeah? Because x1h also have P1. So I still need to differentiate this. So when I differentiate the first term here, let me use the red one. Okay, then the red one here is actually this. So when you differentiate it, I call this one, let's say y, for simplicity. So when I differentiate it, I can use product rule of differentiation. If you can remember your first year study of your undergraduate level, then we have x1h, and then this one is differentiated, this one is constant. Now the next one after plus sign, this one constant, P1 constant, this one is differentiated because it consists of P1 here because we see vector than the x1h, the P1. So that's why you have this and this at the same time. You get me? All right. Now, let me erase this. So, like I said just now, I'm moving to the second line of this differentiation of expenditure function with respect to P1 because I want to find what is the answer. Is it the same as a Hessian demand function for good one? All right. So I can actually simplify the whole thing after the plus sign here. Okay, until here. Okay, as this, the sum of price delta x delta P1, isn't it? The sum of price other prices, okay, or whatever prices including this, times delta xhj and 1. J here refers to other things other than x1h. Other things other than x1h, not including delta x1h. because we want to see this. You get what I mean here? Now, so in this case, instead of writing one by one like this, I have summarized it in the form of summation. That's what I'm doing. All right. Now, here, if you go back to this slide, so you can see this, you can see this. That's what I was doing just now. Okay. All right. Now let's go back to this. Okay. And let's call this as 1. Equation 1. All right. So we write again DEPU DP1. All right. Now, from here, we want to check what's the value of this bit. I'm talking about this, yeah? Is it 0 of the plus sign or not? Or is it something else? How do we get it? By having, by utilizing the envelope theorem from our work here. Okay. We know that, okay, let me show you something here. Recall back the FOC that we get earlier for the minimizing problem to get Hessian demand function is this, isn't it? Until this, isn't it? Remember, our interest just now is to differentiate the expenditure function with respect to P1. Because we want to see, is it going to be, the result is going to be X1H. So let's go back to the FOC that I showed you earlier. And these FOC, first order conditions, are the process in calculating the Hessian demand function. So that means in order to prove the Shepard-Lemma condition here, we need to see the value here, okay, after the plus sign. And in order to do this, we need to use the work that we have done earlier. So when we go through this, we need to look at the Lagrangian function of minimizing process here. And then we did find the FOC for x1, x2 until this, until the last good xn. So we have many of them, but they are of the same pattern. Do you see this? Yeah. And every single of them, if you look here, this one can be rewritten as P1 equals to C delta Ux over delta X1. This one can be rewritten as P2 C delta Ux over delta X2, and so on and so forth until the last one, which is this, which can be rewritten as Pn equals to C delta Ux over delta Xn. So we have a lot actually. So all of these, they have the same pattern, but they are of the same thing. Now, because all of these are in the same pattern, therefore we can write it this way. Yeah, I put it here. So we can have something like this. Pj equals to C delta U over delta P 1. Okay, get what I mean here? Because there are many actually. So in this case, what you can see, let's go back to this. I use different pens so that I can highlight it. You see Pj here. What you can do is that we don't use Pi, we use Pj because we just want to differentiate it between, P1 and also other prices which are not related to XH. Okay, so here I call this one, what's the equation number? Here we have 1 and here we have, let's say, 2. So we need to substitute 2 back into 1. So what do you get? We can have something like this. So it yields something like this. Let me write it again. Delta E PU over delta P1 equals to XH1 plus sum of Pj delta Xj over delta P1, okay, equals to XH1 plus sum of Pj, because Pj we want to substitute this back into this. So you can get C delta U over delta X1, not P1. Yeah, sorry, I have mistake here. Shouldn't be P1. If you look back here, let's go back to this. X1, X2, you get what I mean? Okay, that's why I said I have mistake there. Alright, so this, so delta Xj, that's the correct one. So substitute this into this, delta Xj, and then rewrite again this, yeah, delta Xj over delta P1. Okay, I hope you get it up to this point. Now, and what do we need to do next is that at the same time, after we substitute this, yeah, you see this C is a constant, so I can rewrite it this way, x1h plus C sum of du over dxj times delta xj over delta P1. Alright, I hope you get it up to this point here. So what do we need to do? The next thing is, we are not done, yeah? If you can recall back, I said to you, u has to be equal to ux so that we can get this positive. Remember in our FOC here, let me show you this. Not this one, the second one, which is this. I did explain to you clearly just now, otherwise we cannot solve it mathematically. Alright, so from here, let's call this one number 4, yeah, because I want to have this number 3. Alright, what should we do with number 4 here? Differentiate 4 with respect to P1, yeah? P1. Why we can differentiate with P1 when you don't really see P1 here? We are basically want to find, the Shepard lemma. So the position here has to be at the optimal level. When the position is at the optimal level, that means the x here is also at the optimal level. When x is at the optimal level, okay, then it is a function of parameter prices and utility. Okay, because this is a x that we want to find when we are at the optimal level of minimizing problem. So you can see vector price here. Like I said to you, vector price here consists of P1, P2, until Pn. So of course, you can differentiate this utility function with respect to P1. You get what I mean here? So differentiate 4 with respect to P1, delta U over delta P1 equals to what? So delta U over delta X1 times delta X1 over delta P1. And then plus delta U over delta X1 times X2, yeah? X2 over delta P1. So on, so forth, until the last one, delta Xn over delta U. Sorry, there's a mistake there. This is a lot of numbers. lots of derivation. So delta U over delta xn times delta xn over delta P1. Okay, so instead of writing like this, very long because you have summation, then I can summarize it this way. The summation of delta U over delta xj times delta xj over delta P1. You get me? Alright, now remember this is equals to what? When we do minimizing problem of expenditure, I did mention to you from the beginning that we want to minimize expenditure to maintain the same level of utility. The same level of utility means there is no change in utility after the change in price, and consequently the change in bundle here for good 1, good 2, good 3 when price changes. You get what I mean? And when we do differentiation here, literally it means differentiation means change in utility due to change in price 1. I did mention to you just now, no change in utility when we want to minimize expenditure when price changes, isn't it? So what happens here? Then, because no change, then the utility change here should be 0. You get what I mean? Okay. So here, when this is equal to 0, let me call this one 5. And let's go back to this. Okay, number 3 here. Okay. Can you see? I use yellow. Can you see this bit? Isn't it the same as this bit? Yeah? So what happens here is that we need to substitute 5 into 3. When we substitute 5 into 3, what do we get here? 0, isn't it? So let me rewrite it again here. So it becomes, after we substitute it, delta E delta P1, yeah, equals to x1h plus C summation of this delta U over delta xj over delta P1 x1h plus C times 0 x1h. So it is proven. This is square. My square is not very neat, so but this is a square to show that it has been proven. Alright, so that's proof the property number 7. If we look at the way I proved Shepherd's lemma just now, I said what happens to the expenditures functions when price of good 1 changes. If you look at the explanation just now about Shepherd lemma, when price of good I changes, what happens to the expenditure? Okay, when we differentiate expenditure function with respect to price of good I, then we get Hessian demand for good I. This is what's stated in the slide. But when it comes to example here, we differentiate expenditure function with respect to price of good 1, then we get the Hessian demand of good 1. And in fact, we can make it general, just change it to PI. Everything we change it to PI from the beginning of the process of differentiation here, you can change it to PI so that it becomes tally with the slide here. Okay, now, so we are done with that. Now what we want to look in the next section is the relations between the two. But before that, before I forget, yeah. So when we talk about Shepherd lemma, it's basically tries to state that if you have an indifference curve, or you have indifference curves of the expenditure function, yeah, and these indifference curves are convex, yeah, of course, then the cost minimizing point of a given good, let's say call it good X or Y or whatever, with its price, be it X or Y or whatever, is unique. That means you're going to have one answer. Okay, so here Shepherd's lemma gives a basically precise formulation for the demand for each good in the market with respect to that level of utility, a given level of utility, and those prices. Next, like I said just now, we want to move to the next thing. It's about the relations between the two types of optimization, minimizing expenditure and also maximizing utility. Okay, and here there are close relations between the indirect utility function and also the expenditure function. And both of these functions, the first one here is utility function, which is indirect, and expenditure function, which is also indirect function. Both of them are what we call indirect objective function for consumers optimization, yeah. Because for the indirect utility function, we have direct utility. Remember, the indirect we call it V, the direct utility we call it UX. For the expenditure function here, we have M equals to PX, isn't it? But for this, the indirect one, EPU, isn't it? Okay, so from the definitions of indirect utility function, which is V, and also expenditure function, we know we have these two things. That is, the expenditure function is less or equal to the amount of income for all prices and income which are much greater than zero for all positive prices and income. Yeah. Secondly, the indirect utility function is at least as equal as the desired level of utility, or the targeted level of utility, the given level of utility, which is U, okay, for all prices and also given utility in this dimension, which are positive, yeah. And we can see the sign here are inequality, but then we can always revert from here to here, here to here. Therefore, we can say that both of these inequalities, in fact, must be equalities. Okay, so it allows us to do the, reversion from here to here and vice versa. Okay, so they are interrelated to each other. So this means knowing that the indirect utility function enables us, if we know the indirect utility function, it allows us to calculate the expenditure function and vice versa. And this also allows us to derive indirect utility function as well as in expenditure function without going through a very long process of, optimization problems. What I mean here is first order conditions process. Okay, because they're shortcut. Anyway, because of this, relationship between indirect utility function and also expenditure function, therefore, there are also close relations between Marshallian and Axion demand, and this can be explained in Theorem 6. So in Theorem 6, it says, we have this and these holes. Okay, we have the following relations between Hicksian and also Marshallian demand function for positive prices and also income at least equal to zero, and also for the targeted utility in the set of utility for all goods from good 1 until good n. Okay, and then these relations between Hicksian and Marshallian must hold relation in number 1 and relation in number 2. Relation number 1 here, Marshallian demand function, this one is Marshallian demand function, is equal to Hessian demand function when we have indirect utility function like this. Number two, Hessian demand function here is actually equivalent to Marshallian demand function when we have expenditure function. Okay, so they are interrelated actually. So if you have optimal level of bundle or vectors of goods or commodities, which is called X star, if X star solve the utility maximization problem at prices and also income, it also can solve the expenditure minimization problem at price and given utility, where given utility is actually the same as utility of commodities at the optimal level to achieve certain targeted utility, which is U. Okay, so and on the other hand, if we have a bundle which is an optimal level of bundle, X star, if this X star can solve the expenditure minimization problem at prices and also a given level of utility, it also solves the utility maximization problem at prices, vector, and also income, where income is actually equivalent to the expenditure for the optimal level of bundle or vectors of goods or commodities. Now, so can you see? You can have this, you can have this, okay, inversion. So in this sense, X star here, the optimal level of bundle here, has a dual nature. So we have consumer duality here, and I'll explain more about consumer duality later towards the end of the video, yeah, because in order to explain the relationship between all of this, it's better for you to understand another different concept in the next slide, so that towards the end I can summarize all of this concept in the form of duality. All right, now the next thing is we want to look at the properties of consumer demand. Remember, we have Marshallian and Hessian demand. So when we talk about the properties of consumer demand, okay, we have some theorems here. Let's look at theorem number 7. The consumer demand, which is Marshallian demand function as a function of prices and also income for good I from 1 until n here, is homogeneous degree of 0 in all prices and income. Also, this consumer demand function, which is Marshallian demand function, satisfies budget balancedness. That is, this is total expenditure, isn't it? Price times good, quantity of good in the bundle here, is equivalent to income for all prices and income. So what's the proof here? Actually, we have shown before that the indirect utility function is homogeneous of degree 0 in prices and income. Okay, so if we have the indirect utility function as a function of price and income, this one should be comma, yeah, not semicolon. There's a correction there. So when you multiply, prices and income by a constant, call it T, okay, it still gives you the same indirect utility function like this. Similarly, when you write the indirect utility function in the form of direct utility function like this, but then you specify it further like this, yeah. Then when you multiply the prices and also income by a constant or a scalar, it should give you the same utility function like this. Okay, so that is homogeneous degree of 0. I think I don't have to explain in detail about this because I did mention to you about this concept previously. All right, so we have two different prices and income level. The first one, let's say prices P in the vector of P and also income M, fixed income. And then we have another one in which we multiply these prices and also income by an amount of constant, call it T, then we get TP and also TM. So when we look at budget sets at PM and also at TPM are actually the same, isn't it? So for instance, if this one is 5 and then this one is, let's say, 20, so this one T here, let's say, equivalent to 10, so this one becomes 50, and TM here becomes, you multiply by 10, becomes 200, isn't it? And then they are actually within the same budget set, yeah, because we just increase the price proportionately the same as, and then the income increases proportionately. So when price increases proportionately by the same amount of the proportion of increase in income, then of course the budget sets here are the same. Therefore, the bundle here at price of P and also income of M was attainable also, or was feasible when, we choose, instead of this bundle, we choose this. Okay, was chosen, and vice versa, because it's just a matter of increase in price proportionately, also income increases by the same proportion. So, we don't get another new bundle more. They are just the same, isn't it? Okay. So can you see here, this is the basically what we can say here, the impact of inflation when price also increases. So that's why the first bundle here is just the same as the second bundle. Can you see here? All right. And if you can recall back from the equality, okay, last equality on the previous slide here, which is this, okay, and strict concavity of strict quasi-concavity of U itself, okay, then it allows us to have XPM equals to XTP TM. So X as a function of prices and also income is just the same as a X or bundle X as a function of TP, new price here, and TM, new income here. Okay. So this says that this Marshallian demand is actually homogeneous of degree 0, isn't it, in prices and income? It means when you double your prices and income, okay, doubling the prices and income doesn't actually change the bundle that you want to consume. Okay, so here, and we have the property of budget balancedness that have been proven before. And also when we have this homogeneous of degree 0 here, homogeneity implies that we could focus on relative prices and real income, isn't it? Okay, so for instance, if we have, a number of goods, let's say good N, serve as a numerator. So when I say good N serves as a numerator, we have, good I, good 1, good 2, good 3, so on and so forth, good N minus 1 until good N. And then good N here serves as a numerator, or serves as a, as a measurement of value, or in which prices are measured. Okay, then we may have this Marshallian demand function at prices P and also income M is actually the same as Marshallian demand function when the price and also income increases proportionately by the amount of T right? And then this one actually can be rewritten as this. P1 over Pn, P2 over Pn, until, Pn minus 1 over Pn. This is the second last. And then this one is Pn over Pn, which is equals to 1. And then income over Pn. Now, this is not something new because this one is actually in a very detailed form of this one. X as a function of prices. I call it P prime because, I put over Pn here and M prime here. Okay, so they are just the same. All right. Okay, so, but another more important thing that we need to consider is, okay, how quantity demanded responds responses when price change. Okay, and this, when I say if price changes, it leads to a change in quantity demand. That this is not something new. You have heard it before, and this is what we call law of demand. Okay, you heard it before when you learned in your first year of your first degree, right? And we know that law of demand, increase in the level of price will decrease the quantity demanded of that product. Yeah. But then we also know that this law of demand can be further subcategorized into two different types of effect. The first one is what we call substitution effect, and the second one is what we call income effect. This is what you learn in your first year. So these are the relevant effects that we need to consider when we buy one more good, when prices declines, or when we buy lesser of one good when price increases. Okay. So these kind of relevant, what I call it relevant effects, can be analyzed even in more detailed way when we consider one kind of equation. We call it Slutsky equation. So what does it mean by Slutsky equation here? So it can be explained by theorem 8. Let's say Marshallian demand function acts as a function of prices and income. Okay, is this one. Now let U star, the direct utility function, okay, be the level of utility the consumer achieves at prices P and income M. Okay, then we have this Slutsky equation. Now Slutsky equation says that if we differentiate the Marshallian demand function of good I with respect to another good, call it good J, with respect to the price of good J, then what we get here is on the right hand side of equal sign. So we get this. So you can see here it is equal to the differentiation partial derivative of Hessian demand with respect to price of good J, Hessian demand of good I with respect to price of good J, minus Marshallian demand of good J multiplied by partial derivative of good I with respect to income, such that I and J are good from 1 to until n. So after the equal sign here, the first thing here is what we call substitution effect, and after the minus sign here is what we call income effect. Now we always learn that if price increases for good, let's say good I, okay, and then quantity demanded decreases for good I, isn't it? Okay, now, but then how much it increase or decrease here is not always, it's a question actually. Why? Because sometimes you can see even if the price increases, people still want to buy more, isn't it? So there must be something in between. So we have to look whether substitution effect outweighs income effect or the other way around. So that's why Slutsky equation is very, very important. Right, now, but before we go into detail here, let's prove the Slutsky equation. Now, before we prove the Slutsky equation, you look at U star here. U star here is the direct utility function that is at the optimal level. So if it is the direct utility function at the optimal level, let's say we have two goods, X and Y. Okay, so we have this, isn't it? So X and Y that we consume is at the optimal level that give us the best utility. Then this one is actually equivalent to the indirect utility function. Okay, this is basic in the first video, yeah? So let's look at the proof. So we start from the identity of, we already know this, Hessian demand function when utility is at the optimal level, this is utility at the optimal level, is actually equivalent to the Marshallian demand function when for given prices and expenditure when utility is at the optimal level. So if you see here, it is actually this, okay, M. Why do we call this? Because one thing that you need to understand is when we reach optimal level of utility, the best one, the one that's give us the maximum level of utility, whatever we spend here, okay, is actually equivalent to income. We don't spend less, we don't spend more. Okay, so that's why here the Marshallian demand function, usually we write it this way, isn't it? Okay, but because at the optimal level the total expenditure here is equivalent to income, then we substitute it by E here, right? Now remember, we want to come up with the Slutsky equation. What we need to do is that with this expression, let me erase this one so that it won't be the mess. So we need to differentiate this identity with respect to price of good J. And when we differentiate it, we get something like this. Remember, yeah, this one is actually X as a function of prices and M. So you see here. So when we differentiate the left-hand side with respect to PJ, then we also need to differentiate the right-hand side with respect to PJ. Now, before we differentiate the right-hand side with respect to PJ, you see here, like I said just now, the right-hand side is actually the Marshallian demand function, but at the optimal level of utility, call it U star. And because it is at the optimal level of utility, therefore, the expenditure is equivalent to income. So I just, replace it, Marshallian demand function with a, as a function of M with E here. So let's go back to this because we haven't finished differentiating the right hand side. We haven't done it at all. Okay, now, so remember we need to differentiate both sides with respect to Pj. This is vector P. In P you have P1, P2, P3 until Pn. Let's call P1 here, Pi, the rest are Pj. Okay, either one of the rest here are Pj. So that means you need to partially differentiate the Marshallian demand function with respect to Pj for this one first, yeah? And then after that, you need to differentiate the Marshallian demand function with respect to expenditure here. So differentiate the Marshallian demand function with respect to expenditure. And because like I said, expenditure here at the optimal level is equivalent to M, instead of writing delta X over delta E, we can also write it delta M, isn't it? Because they are just the same. And in M here, because M is equivalent to EP U, isn't it? Okay. In M here, because M equals to E as a function of prices and U, and we know that P here is this. And we know that we are differentiating the whole thing with respect to PJ. Therefore, we need to differentiate M here with respect to PJ. Why? Because in M, at the optimal level, which is equivalent to E, contains P. Okay, so dx over dm multiplied by de over delta x over delta m multiplied by delta E over delta Pj. That's it. Now, this is not the end of the proof because we need to show the Slutsky equation has something like this, okay, looks like this instead, so that we can see clearly which one is substitution effect, which one is income effect. Right. Now, how to do this? Then we need to use whatever information about theory and also mathematical theorem that we learned from the previous direct and indirect utility function, direct and also indirect expenditure function. So one of the theorems that we could use is Shepard's lemmas. And we already know that from Shepard's lemma, we have this. Okay, Shepard's lemma says, let's recall back what Shepard's lemma says. Shepard's lemma says if we differentiate the expenditure function with respect to a price of one good, let's say in this case good J, okay, then we get the Hessian demand function for good J. In this case, because we are talking about the optimal level of utility, we are differentiating the expenditure function at the optimal level of utility, call it U star, with respect to price of good J. And then we obtain, based on the Shepard's lemma, we obtain the Hessian demand function for good J for given prices in vector P, as well as optimal level of utility, call it U star. And because the optimal level of utility says that we have expenditure equivalent to income at the optimal level, and at the same time, Hessian demand is also equivalent to Marshallian demand at the optimal level of utility U star. Therefore, this Shepard lemma here is also equivalent to this Marshallian demand function for good J at the U star level of utility, at the optimal level of utility. Not only that, when we have the optimal level of direct utility function, that means it is actually equivalent to the indirect utility function for a given prices, a vector, and also income, isn't it? Because indirect utility function, if you can recall back in video 1, the first one, it is actually, the utility at its optimal level. And this one, you already know, yeah? So we actually, because this one is U star, we substitute it to the indirect function of utility, then we can get this. All right, now this is not the end. We still need to, get to the proof. So here, using these two conditions, okay, what we can get is the next line. So as you can see here on the left hand side, stay the same. Now, on the right hand side, we substitute expenditure function at given prices, okay, and also utility optimal level. Because expenditure function at the optimal level of utility is equivalent to M, we substitute it by income M here, okay. And then this one, okay, the denominator stay the same. You see here, we substitute it by M also. This one we already knew. And then this one we also substitute by M also. Okay. So because E, P, U star. Initially it was E, P, U star. Initially it was E, P, U star. You get me? Alright. Now, rearrange it mathematically, bring left hand side to the right hand side and whatnot. We get the final expression. And this one is actually Slutsky equation. Now, Slutsky equation, okay, you can see clearly the first bit here is substitution effect. If there is a change in the price of J, what happens to the Hessian demand of good I? So that's the substitution effect. Income effect is this one. Alright? So intuitively, when we talk about substitution effect, hypothetically, it is actually the change in consumption that would occur after prices were set to the new level, or in other words, in the simple way, after prices change, yeah. But where income was adapted such the maximum level of utility the consumer can achieve were kept the same, or in other words, we have the same maximum level of utility without change, even if price changes, okay, as before the price change. Okay, so this is Hessian demand. And income effect, okay, it's actually a change in consumption if prices were to keep at the new level, but income was set back to its real value. Okay, so that's the Slutsky equations intuition. So by decomposing the total effect of a price change, this is a price change, effect of price change on the demand, Hessian demand of good I. So when we decompose it this way, okay, into substitution and income effect, it is very useful because we can now we are able to characterize the single effects in more detail. Okay, so here it leads to the next one. We call it theorem 9. So theorem 9 says, let's say XH as a function of prices and also utility be the Hessian demand for good I. And then we can have partial derivative of Hessian demand function for good I with respect to its own price is actually less or equal to 0 or negative. Okay, so here on substitution terms are negative. How to prove it? We can use a Shepherd lemma here. We know that Shepherd lemma says in order to obtain Hessian demand function, which is this, we need to differentiate the expenditure function with respect to the price of good I. Let's say this one is Hessian demand function for good I. Yeah? Okay. Now, what we need to do is, because we need to prove that this one is negative, yeah? So that means we need to differentiate this with respect to its own price, Pi. So you differentiate left-hand side and also right-hand side, again with respect to Pi, what you get is this. Okay, what you get is this. If you can recall back, the expenditure function is concave. Okay, see the previous slides. Yeah, I did mention to you in the previous slides. When it is concave, you imagine that the graph looks like this, isn't it? So when the expenditure function is concave, but it is still increasing, isn't it? Can you see here? So when it is increasing, that means the slope is positive. The slope of expenditure function with respect to the price of good I is positive. Okay? And the slope is given by this. Okay? But because we want to differentiate the left-hand side and also the right-hand side with respect to Pi, that means we need to differentiate this slope with respect to Pi again. Then we get this. Now, how do we know this bit is negative? So that we can prove the Hessian demand function, when we differentiate it with respect to its own price, is negative. How do we know that? Like I said just now, you already know that expenditure function is concave, upsloping and concave. But when it is concave, the slope is positive. That means this one is positive. But when you differentiate it once again, okay, let me draw it properly. When it is concave, you can see here, when you move from here to here, the slope is still positive, isn't it? But it becomes flatter and flatter. That means the second derivative here is negative. Okay? The slope is increasing at decreasing rate. Slope is increasing for expenditure function with respect to Pj because this one is positive. At decreasing rate because the slope becomes flatter and flatter. Second derivative is negative. So because second derivative here is negative, this also equals to this after we differentiate both sides, then we know that from this information, this one is negative. Then it is proven. Okay? Now, let's look another thing here because all of this has something to do with, law of demand and whatnot. Definition 11. A good is called normal good if consumption of it increases as income increases, holding prices constant. This basic definition, you have heard it in your first year of your first degree. Also, look at definition 12. The good is called inferior good if consumption of it declines as income increases, holding prices constant. Also, you have heard this before. Normal good, inferior good. Have you heard the term given good? All of these are basic principles, so please check it out from the YouTube and whatnot if you forgot it already. So I'm not going to re-explain it again to you when it is already a basic thing in the first year of first degree. So here, from the two theorems derived previously, and the definition that we have in definition 11 and 12, so it's very easy to derive law of demand. And when we talk about law of demand, let's look at theorem number 10. Theorem number 10 says a decrease in the own price of a normal good, will cause quantity demanded to increase. So law of demand, where we have negative relationship between price and also the good itself, price of the good and the good itself, is always negative when it is considered as or characterized as normal good. Okay, so if an own price decreases causes a decrease in quantity demanded, then the good must be inferior good. So can you give example what are the examples of inferior good? What are the example of given good? What is the example of normal good? Okay, now the law of demand connects concepts about reactions of quantity demanded to income changes with concepts about directions of quantity demanded to price changes. The last part is to look at some very useful elasticity relations, and then these kind of relations can be derived from the budget balancedness constraint. So when we say balancedness constraint of budget, it's actually total expenditure equivalent to total income here. Okay, now let's look at definition 13. Let's say we have Marshallian demand function for good I, which is this. So denote as eta. Eta is actually the income elasticity of demand for good I. And how to find the income elasticity of demand of good I, or call it eta? You differentiate the Marshallian demand function with respect to income, and then multiply it by the ratio between income and also Marshallian demand function. This one is not something new yet. If you can recall back in your first year study, the first one here, the first bit here after the equal sign is actually what you saw in your first year is this. Change in quantity over change in income multiplied by income over quantity of good I. Okay, so this is what you saw when you were in the first year. But because we use proper mathematical equations, therefore we use differentiation here, derivative, partial derivative. Now let's look at the second one. Epsilon ij is actually the price elasticity of demand for good I. Okay, price elasticity demand of good I, that is differentiate the Marshallian demand function with respect to price Pj. Okay, and then multiply by the ratio between price Pj and also the Marshallian demand for good I. So if we know the price elasticity of demand for good I here, we can measure, whether it is elastic or inelastic, and also in terms of substitutability of one product to a price. Okay, a price of its own or a price of other products such as product J. Now let's look at number 3, SI. SI is actually the income share spent on purchases of good I. So you see here on the numerator is actually P times XI, isn't it? Price of I times XI, good XI, quantity of good XI. Well, good I, So here, this one is actually total expenditure spent on good I divided by income. So actually, if we have income, our income consists of P1x1 plus P2x2 plus until the last good Pn xn, isn't it? But if we take this, divide by this, then it becomes the ratio between total expenditure of good I, good one, in this case good one, over income. Let's say good one here is good I. So it becomes the income share spent on purchases of good I. Alright, now the next thing is to show you the concept of consumer duality in the form of summary. But before that, I want to fix some mistake here. Let's go back to this. Okay, when I tried to show you the derivation of Slutsky equation, the proof of Slutsky equation, all of the mathematics here, written here, are all correct. But when I say it, I did mention to you, differentiate the expenditure function with respect to good one. It's not with respect to good one, it is with respect to P1, the price of good one. So that is the correct way to say this one. but the writing here is correct. Okay, so all the writings are correct except the way I mentioned it last time. So the correct way is differentiation of expenditure function with respect to price of good one. Okay, so this is about the correction in the the explanation of proof of Slutsky equations. Now the next thing, like I said just now, is to show you the summary of the relationship of between the utility function and also the expenditure function. And this can be done by looking at the concept of consumer duality. So let's look at it now. Whenever we talk about consumption duality, remember, any individual consumer's decision has dual nature. So consumption duality actually can be solved either by having utility maximization or expenditure minimization. We can have, for instance, fixed budget and then obtained the maximum utility. And this is what we call primal problem. Okay, primal problem. Or instead of fixing budget, we set a level of utility. Okay, fixed it and then minimize the expenditure. And this is what we call dual problem. Okay, so this is primal problem. Now, when we talk about primal problem in mathematics, if you can recall back, so we're actually maximizing utility of consumption of bundle X or vector X goods subject to total expenditure, which is less or equal to income. On the other hand, if we talk about dual problem, then we are minimizing total expenditure here subject to utility of consuming a certain bundle of good, call it bundle X or vector X, to fulfill the amount of targeted utility we want to achieve. That is U here. Okay. However, if you look at these two, you look at the sign here, this sign, it is inequality, isn't it? So these general equations are modified a bit so that they are more suitable for real-world application and graphical presentation. And we modify it so that it is easier to solve this optimization problem by looking for equality. So instead of writing this, let me change the color. Then we use this. That's why you see when I gave you example, I always use equality sign, isn't it? If we don't have this equality sign, we want to solve like this, then you need to go through the Kuhn-Tucker problem and you need to find the corner solution, mathematically speaking, yeah? Okay, so it is easier to solve this optimization problem by looking for equality rather than trying to solve inequality. Now, in the form of graph here, let's say we have two goods, x1, x2, okay? If we talk about primal problem, this is budget line, okay? And then this is utility. So, in the primal problem, if we know utility and budget line, we can find the optimal level as as in the graph here. And that optimality is here, isn't it? Let's call this point A. Okay. But then, for most purchases, we don't have fixed budget. Okay. We have certain utility that we expect to derive from, budget here. And we try to spend as minimum as we can to achieve it, isn't it? We have expectation to feel happy. That's what I mean. Okay. So here, for the dual problem, we fix utility. And then we can play around with cost. So here, we opt to spend as little as possible or as minimum as possible to reach the desired level of utility. Let's say we want this utility, so we try to spend as minimum as possible. Okay, so note that the dual problem can be solved analytically using a series of substitution and theorems. Okay, let me erase this first so that I can show more here. Let's erase this graph. So like I said just now, the dual problem can be solved analytically using a series of substitution and theorems. The first thing is that we know that by solving the primal or dual problem here, we will end up getting Marshallian or Hicksian demand function respectively, isn't it? So for instance, if we have a primal problem here, erase this red pen first. Subject to this budget constraint, then we can end up with Marshallian demand function, in which Marshallian demand function is a function of prices and also income. When we try to solve dual problem, we can end up with Hicksian demand function, which is a function of price and fixed utility. The Marshallian demand function here is also known as uncompensated demand function. And therefore, Hicksian demand function here is known as compensated demand function. And then we know that once we get the Marshallian demand function, if we substitute certain variable, okay, we can get another thing here, that is indirect utility function. Okay, indirect utility function here. So if we substitute the optimal variable in the primal problem, so here, when we do the optimization here, we get this, isn't it? And then once we get this, we substitute it back into this, then we can get indirect utility function at the optimal level of utility here. That's what I mean. Okay, let me erase this first, otherwise it becomes a mess. On the other hand, if we look at the dual problem here, from here, we get the optimal level of Hicksian demand function. So if we substitute the optimal level of variable in the dual problem here, okay, in the second one here, we get the expenditure function, isn't it? Which is this, as expenditure function is a function of prices and also fixed utility in such a way that at the optimal level, this expenditure is equivalent to total income. All right? So I hope you can get it up to this point. And then, the next thing that we can realize is that all of these equations actually have few tricks and similarity that can be used in order to move from one to another. Okay, what does it mean here? For instance, if we have Slutsky equation, so we have Slutsky equations. Okay, recall back what's the Slutsky equation. I'm not going to write it here because it becomes a mess in this whole, simple, graph here or simple chart here. So if we have Slutsky equation, we can use this Slutsky equation to relate what? To relate Marshallian demand function and also Hicksian demand function. And then when we have Slutsky equation here, it helps us to determine the types of good to be analyzed. And secondly, it allows us to determine income and also substitution effect. Secondly, we can also invert utility and income to obtain what? To obtain the expenditure function from the indirect utility function or vice versa. All right, now let me erase this first because I need to explain the next point. And then we can also use substitution to get the demand function using indirect utility function. In particular, let's say if we substitute the indirect utility function in the Hicksian demand function, now this is the indirect utility function, isn't it? Let me use yellow color. So if we substitute the indirect utility function in the Hicksian demand function, go here. This is Hicksian demand function. Then from here we get Marshallian demand function. You get me? On the other hand, let me use other color. All right. If we substitute the expenditure function, this is expenditure function, isn't it? In the Marshallian demand function, now what do we get? We get Hicksian demand function. So, recall back, we can work backward from indirect utility function. Which one are the indirect utility function? Indirect objective functions, yeah? Indirect objective functions to get Marshallian and Hicksian demand function. Now, where are the indirect objective function? Indirect objective functions are this and also this, because these two are indirectly derived from Marshallian and also Hicksian demand function respectively. All right, now, so if we can work backward, yeah, from the indirect utility function and also expenditure function to get Hicksian and demand function. What does it mean? In particular, look at the indirect utility function here, this one. We want to work backward. If we differentiate the indirect utility function with respect to P when utility is constant, when utility is constant at the optimal level here, okay, then we can get Marshallian demand function. We get it, by having Roy's identity in it, okay, to obtain Marshallian demand function. Similarly, look here. Okay. If we differentiate the expenditure function with respect to price, okay, we can have what we call Shepard's lemma in order to obtain Hicksian demand function from expenditure function. So here, consumption duality can be seen as what? Here, consumer tries to maximize utility subject to monetary constraint. Okay, if we are talking about this is the monetary constraint, isn't it? Or consumer try to limit their expenses or costs subject to their targeted or desired utility level. So either way, either this one or this one, okay, can be solved, especially if we correctly or properly calculate the Marshallian and also the Hicksian demand function. So that's the consumption duality. So you can see here at the optimal level, both maximizing utility and also minimizing expenditure here subject to their own constraints respectively are basically the same in abstract way. They are the same, okay, as long as you know how to go backward from here to here or here to here, or as long as you know how to relate between Marshallian demand function and also Hicksian demand function. All right. Now, if you think that this is not enough, let's look at the examples. Here, I want to show you one very simple example of how to derive Hicksian and also Marshallian demand function from optimization. So let's say we have utility function given as this, U is equal to x times y. So we have two goods here. This is the simplest case, yeah. The simplest case, that is, we have two goods, x and y. And then we have the budget constraint subject to px times x plus py times y, and then equals to less or equal to income, isn't it? But because we want to utilize all of the income, then we equate it equal to income. Now, as usual, from this direct utility function, I want to come up with Marshallian demand function. My method here is I just show you a very important a thing, but I won't show you how to get to the final answer. I may give you the final answer, but I won't show you in between how to get it, because this is just the matter of calculus which you have learned in the high school. So don't expect me to explain everything. But when it comes to exercises, you have to show every single step of the work. All right. What we need to do here is to set the Lagrangian function. So Lagrangian function here is xy plus lambda, this is the multiplier, times m minus px times x minus py times y. Okay, so as usual, we need to find the FOC of first order condition because we want to maximize utility subject to this budget constraint. So differentiate lambda with respect to good x, we are going to get this y equal to y minus lambda p x equate it to 0 because this means first order condition. If you just do this bit, this is the first derivative of Lagrangian function with respect to x. It's not the first order condition. The moment you equate this derivative to 0, that means it is a first order condition, and this one is called optimization because we want to maximize. So when we maximize, when you have utility function which is convex, okay, maximization here, this one must be tangent, isn't it? This is what I mean. Let me redraw again this. Then the budget line here must be tangent to the IC curve. So if we turn it upside down, then the maximum point is here when the slope or the first derivative, which is this, is equal to 0. So the same thing we do for good y. Then you can get x minus lambda p y equate it to 0, and don't forget to differentiate the Lagrangian function with respect to the multiplier, which is lambda. Then we get m minus px times x minus py times y equal to 0. So when you solve it, this one, you can get something like this. So I skip the step, but you need to know how to do it. But when I skip the step, you can't skip the step in the assignment, yeah? Okay, so from here, when you solve it, substitute it into the budget constraint here, then you can get this. Okay, so you have the Marshallian demand function for x, which is a function of price and also income. That is m over 2p x. And then you can have Marshallian demand function for good y, which is m over 2p y. Okay. Now, from here, we can have what we call indirect utility function. Indirect utility function is a function of price and income, which is equivalent to, U star equivalent to x star, y star. And x star, y star here is this one, okay? So I can put star here, I can put star here. So when you simplify it, but you have to show it, yeah? So you get, this one is the final answer. I just skip it, but you can't skip. How to get this? You must know how to get this. So you get 4p over m over 4px times py. But how to get this? You must show it step by step here. So this is the indirect utility function. Now, imagine if we don't know this direct utility and this budget constraint, but we are only given the indirect utility function like this. But then the question asked, from the indirect utility function here, the specific one here, how to get the Marshallian demand function for good x and y. So here you already learned that you can use the shortcut way. We call it Roy's identity. And Roy's identity says what? You take the partial derivative of indirect utility function with respect to the price of good x, for instance. Let's say we want to get the Marshallian demand function for good x. So take the partial derivative of this. Don't forget to put minus sign. And then take another partial derivative of indirect utility function, but this time with respect to m, take this ratio, that you get the Marshallian demand function. Okay. So how do we do this? This is very simple. So delta V over delta Px is actually what? Let me rewrite again the indirect utility function that we already found earlier. This is actually m squared over 4px py in it. So when you differentiate it with respect to x, m here constant, 4 constant, py also constant. Then we get this. Okay, this is a very simple differentiation for px squared and then py. Okay, you need to go back to your basic differentiation in your first degree level, because this one I'm not going to show you how to get it. This is a very undergraduate level. Okay, now if you differentiate the indirect utility function with respect to m, this is very simple. It becomes 2m over 4px times py in it. So when you simplify it, you get m over 2px py. So combine these two in this ratio to get the Marshallian demand function, which is what? So here we have minus, and then we have minus from this, and then this minus comes from this, isn't it? So minus minus m squared over 4px squared py, and then over m over 2px py. When you simplify it, this is very simple already. And here, this 2 gone, this becomes positive, this gone, this becomes 1, this gone. So when you simplify it, then it becomes m over 2px. So this is the Marshallian demand function. So if you check this with the one that we get earlier, and they are the same. Okay, so why don't you try at home to get the Marshallian demand function for good y. So you need to change the differentiation here a bit, because now it's no longer with respect to px, but now with differentiate the indirect utility function with respect to py. Okay, now what about if we, instead of getting indirect utility function, we want to get the expenditure function. Now recall back the indirect utility function case here. When we want to maximize the direct utility function with respect to budget constraint, we put income constant and prices constant, but we allow ourselves to find the maximum level of utility for a given income. On the other hand, if we want to find the minimization of expenditure, this time we want to find the minimum cost or expenditure that we can have, okay, for a given utility that we want to achieve or we are desiring. So let's look at this now. So we still have u equivalent to xy. We still have, income equals to px times x plus py times y. So we want to minimize px times x plus py times y, okay, equals to or less than income, subject to u equal to x, y, okay. And that u here is the desired level, and the desired, let's say here, this is the utility that we use to achieve satisfaction with the consumption of x and y, and we have a targeted utility, and that targeted utility, call it u naught. So this has to be equal to this, or this has to be bigger than this. You get what I mean here? Or equal, bigger or equal, yeah? So let me rewrite it again properly now. So in this case, that means subject to what? Subject to u naught greater or equal to xy. This one is u, Okay, so this is the targeted utility. This is the utility that we use to achieve our satisfaction when we consume two goods, x and y. All right. Now, as usual, we need to set up the Lagrangian function. Now, this time the Lagrangian function is px times x plus py times y. Okay. Plus, I put the multiplier. In order to be different, I use different Greek letter, which is C. You can also use other types of Greek letter. And multiply by u naught minus xy. Because, like I said in the previous slide, when I talk about the consumer duality, it is easier to solve it using equality rather than inequalities. All right. So, as usual, you need to find the first order condition. We want to minimize, this budget subject to utility constraint. In this case, utility constraint here is that we are having a targeted utility which is me naught and not other level of utility. So utility level is constant, but here we play around with the cost. So it means the cost can change to achieve the desired level of utility. So we want to find the optimal level of cost that is the minimum possible to achieve this level of utility using this, combination of goods here. Okay. So differentiate Lagrangian function with respect to good x. You are going to get this. Px minus what? Minus cy equals to 0. I hope you already understand the concept of 0 and the concept of derivative here, partial derivative. I won't explain it again. Now, differentiate L with respect to y as well. You get py minus cx, equate it to 0. This is the second first order condition. And don't forget to differentiate the Lagrangian function with respect to c here, the multiplier. Then we get something like this, me naught minus xy equals to 0. So the constraint here is binding so that we can do the, we can do the calculation. So from here, we know that me naught equal to xy. Now from here, you can get the ratio of px over py. There are some steps in between to get this ratio. You must show it. Then it is actually equal to y over x. Okay, so in order to find the Hessian demand function for good x and y, after that you're gonna see that you are going to arrive to this solution. Hessian demand function is a function of prices and a given utility, so call it mu naught. And then this one later, once you solve this, first order condition problem of, you substitute it into this, then you can get Hessian demand function for good x, which is equal to me naught py over px, the whole thing square root. Okay, and for good y, I don't have enough space, so I write it here. For good y, the Hessian demand function for good y is written as me naught px over py Let me erase it because it's not very clear. So px over py, the whole thing square root. Okay, the whole thing square root. So that's the Hicksian demand function for good x and good y. Now from here we can create what we call expenditure function. The expenditure function, remember, we already have the Hicksian demand function for good x and good y. That means we already achieved the optimality of good x and y that can minimize the cost. So when we write the expenditure function, this expenditure function here is the minimum expenditure function that is required to obtain utility at me not. And when it is minimum, it is the optimal level. When it is at the optimal level, it is equivalent to income level. And we already know that income level here is actually equivalent to P x times x plus Py times y. So it's equivalent to Px times x plus Py times y. So we x and y here at the optimal level are basically Hicksian demand function for x and y. So here px, because I want to obtain the expenditure function, times u naught py over px square root all of them in the circle bracket plus py in the circle bracket u naught px over py, the whole thing square root in the circle bracket. When you simplify it, there are some steps here, algebraically speaking. I'm not going to show it because this is a very basic undergraduate level of mathematics. Not even undergraduate, it is a high school level of mathematics. So you should get something like this. 2 times mu naught to the power of half or square root px square root. Okay. And also py square root. Okay. So that's the answer for it. So from here, let's imagine you don't even know the utility function, the direct one, and also the budget constraint here. And you are only given the expenditure function, the optimal level, which is this. So E Pu naught is this. You are only given this. Then the question asked is, find the Hicksian demand function for good x. So what should you do? Then you should use Shepherd lemma. Okay, Shepherd lemma. And Shepherd lemma says, when you differentiate the expenditure function with respect to the price of the good, let's say we want to find the Hicksian demand function of good x, so we differentiate the expenditure function with respect to the price of good x, we should get back the Hicksian demand function for good x for a given utility. Okay, so what you need to do is you need to differentiate this with respect to px, and then you should be able to obtain mu naught half square root px minus half to the power of minus half, and then py square root. Okay, so try this because this is very easy. I just go straight to the final answer. Okay, but the differentiation here is very easy to do. You just need to differentiate this function with respect to px. Now let me tell you something. If you don't understand, or if you forgot already how to do differentiation, the basic differentiation, you must try with your own initiative, taking your own initiative to look at YouTube or the basic maths books or the lecture notes from the internet or from any kind of textbook on the basic thing of differentiation. There are a lot actually. So this can give you more insight on how to do differentiation. At your level, we don't teach you how to do differentiation. Otherwise, this class or this module would be, mathematics module instead of microeconomics. We are more into analyzing the use of mathematics in economics here. All right, now you have seen that how Roy's identity and also Shepard's lemma can give you ways to find or to move backward to get the Marshallian and also Hicksian demand function from from the indirect utility function and also from the expenditure function respectively. Recall back when I talk about the consumption duality with the primo problem and also dual problem, I did mention to you that you can get, when you have indirect utility function here, you can do something with the Hicksian demand function together with the indirect utility function to get something else, isn't it? Remember what did I say earlier? So please, here in the exercise here, I only explain up to Shepard lemma's application. So you must go more than this to understand more about the concept of consumption duality. There are a lot of examples that you can find from the internet basically. Okay, so that's it for this topic. Is a long topic. Consumer theory is a long topic. This part 2 is very long as well. But if I were to, segregate it or categorize it into smaller parts, then it becomes broken. Because I need to explain it, continuously. But you can see from different YouTubes, they try to segregate it into smaller parts, which is okay also. So those things on the from the internet can also be a complement to the lectures that I have in this video. The best thing for you to study is, first, listen to this video. Second, write your own lecture note from this video. And then if you don't understand, refer to some of the YouTubes. If you still don't understand, refer to the simpler part of the YouTube. And then try to figure out specifically what you don't understand. Okay, then you can send me email asking me questions. There are some students who try to send me email asking question, but they are not very specific in terms of asking question. So when you're not very specific in terms of asking question, the way you write question is as if that you want me to re-explain the whole thing again, when you can always watch the video all over again. Be specific which bit you don't understand. For instance, let's say we are talking about this minimizing total expenditure here with respect to, subject to a given utility or the targeted utility function. When you don't understand why we need to have FOC or first order conditions here, that means you don't understand the concept of conditions, first order condition. But you may understand how to get answers such as Px minus Cy or Py minus Cx, isn't it? Because this is just basic math. But you still don't understand the concept of FOC. Then you can ask me this way. I can understand how to derive the answer for Lagrangian first order condition, mathematically speaking, but I don't understand why we should equate it to 0 when we do minimization. Then from there I can understand you know the mathematics, but you don't understand what does it mean intuitively. Why do you do this? Then I can explain it. But some students, when they tell me, I don't understand when you do the first derivative. In what sense? It could be, the way you ask me, I could interpret it this way. Number one, you don't even know how to do differentiation, which I won't entertain. Number two, are you asking me about the concept of first order condition or partial derivative only? Because these two are totally different things. Okay, so be more specific. So that's why some students, when they ask me questions, if it is not very specific, I will not entertain. The best part is, if you ask any lecturers around the world, if you ask very general question, then what they will do is that they just ignore you, to be honest with you, because as if that you are asking them to explain from A to Z once again. Okay, so be specific. So you must be creative enough to ask questions so that people can entertain you. You yourself put yourself in our shoe when you are asked to do everything all over again, okay, by somebody. Would you do it? Okay, so this is the thing that you have to understand. We can appreciate you if you ask specifically, because we know that which part you don't understand. We know that you are really struggling. We know that you are really studying. You get what I mean? So if you just say that I don't understand the slide from 47, let's say this slide, from this slide and this slide and this slide and this slide and this slide, for instance. So it's like, the whole thing. I don't think that the whole thing, because of course there must be something inside here that makes you cannot understand. So be specific. Which bit? This one, why it is related to this? You get what I mean here? So I hope you guys can be, more constructive when you ask questions. So all the best. So that's it for Consumer Theory Part 2.